A check one, two, a check one, two. You got Husky on the mic. Is Husky on the video? Hey, hello, everybody. Hello, and thank you for having me on. I'm very excited to be a guest here. So, yeah, let's have some fun. Let's do this. I want to say one moment. Let's get a voice check on our good friend Taggart here.
Oh, whoop, there we go. Let's try that again then.
How we doing?
All right. You can probably
I
hear
was
me now
saying
because my
what he
microphone
was
is
saying
unmuted.
is what he was saying is absolutely eloquent and articulate and amazing. But let's take it back and let's do it one more time.
Yeah. A lot of spinning plates with a guest, so thank you
Yep.
for bearing with me. But yes, welcome to Saturday Hacker Day. As you obviously already heard, my name is Taggart, and with me is Husky. And because he's joining us for the entire stream, we're going to get to do the cyber news this week. So up first is a vulnerability in Azure's Active Directory authentication mechanism that allows brute forcing of accounts without any lockout whatsoever. Um, this is getting a lot of play in the security research press, a lot, especially folks like Daniel Card and Nathan McNulty, folks who really focus on Azure authentication issues and Azure in general. And here's basically what's going on. For legacy Exchange authentication, there is a specific path for authentication through Azure Active Directory that uses a password-based authentication, no MFA, and multi-factor authentication. And what it will do is it will then chain into a Kerberos authentication mechanism using Azure Active Directory. But on the end, on the API end side, where you're attempting the authentication, all you get is either a success or failure, and so you can then brute force passwords for a given account to see if it is successful. And there's no lockout, and there's no logging. This successful event is logged, but the failures are not. And
Ouch! Ouch!
consequently,
Ouch!
the visibility on this is really terrible. And Husky, you and I were talking about how this sounds a whole lot like another attack path that we've seen with Azure authentication brute forcing.
Yeah. So, you just cloud or not or on-prem or not, it seems like you really just can't get away from this certain type of like API authentication brute forcing or API authentication attack. This seems a lot like an attack against Exchange and EWS, right? So for if you're not familiar, when you stand up an Exchange server, there are lots of different APIs that kind of sit internet facing that clients can interact with. One of those is the EWS, and the EWS can be brute forced. You can whip up basically a little script to interact with the API and send requests to it and enumerate users. You can dump the GAL that way. So it's a unfortunately, it also does not allow for multi-factor authentication. So it just seems like, in short, what is old is new again. It seems like this keeps happening because Azure is supposed to be kind of like the answer to on-prem, like, hey, get away from on-prem and go move into the cloud. But with sufficiently complicated systems like this, you're not gonna be able to get away from, these ugly little API brute forcing bugs that seem to work their way into the system.
Absolutely. A couple of other points that I wanted to touch on with this one. So there is another attack path that we know for Azure brute forcing, which is using the Microsoft Graph API. If you're not familiar with the Microsoft Graph API, basically, inside of Azure, Graph API is the thing that relates all entity data inside of Azure to everything else. And so if you make queries to the Graph API for specific users, that's how you could go find related contacts, or you could find associated accounts, or even Azure objects that that user has permissions to view. It's a really powerful API. However, attempting to authenticate to the API is a way to brute force account credentials because, again, it'll give you a failure or success, but not a lockout. And so it's really, really nice once you have even some credentials, either through, open source tools like Hunter.io or something else, or even your own OSINT research. Um, Once you have that and you know that it's an Azure shop, you're able to go in and use the Graph API to start brute forcing creds. Project TP, Richie, good to see you both. And then the other point I wanted to call out was, generally speaking, what people are doing in a hybrid environment is you have Azure Active Directory, which is a mirror plus Azure stuff, but a mirror of what you have on-prem. In order for authentication to work between the two of them, you basically have two choices. One is called password hash synchronization, whereby the NTLM v2 hashes are synchronized up to Azure Active Directory. In this scenario, the passwords themselves are not actually stored in Azure AD, just the hashes. And so what happens is you check against Azure AD for anything that is in the cloud. You're checking against Azure AD for that hash match, which means that those hashes are there and capable of being disclosed somewhere through Azure AD. That's scenario one. Scenario two is something called pass-through authentication, whereby it is a direct pass-through. Nothing is stored in the cloud. It's Azure AD making a phone call home to the on-prem domain and getting the authentication decision from the on-prem domain controller. There's option 3, though, which is no on-prem domain controller, and you're running everything in the cloud, in which case the keys are in the cloud. And that's what's really alarming about this situation, because what's going on in the back end after this email authentication happens is all of a sudden a Kerberos process kicks off inside of Azure Active Directory. And so like everything is available, and if you get through, right, there's nothing stopping a traditional Active Directory kind of pivot situation, but in Azure, which we know in environments using situations like that have decreased logging because logging costs money in Azure.
Yeah, ouch. Ouch across the board.
It's real
ouch
bad.
for logging, ouch for cloud resources tied into on-prem resources. Ouch for the fact that like I said, cloud is kind of supposed to be the answer to on-prem. Cloud security is kind of marketed to be the answer to on-prem security. But it seems like what's old is new, and you can't really get away from these kind of Exchange vulnerabilities. Certainly, Active Directory vulnerabilities are here to stay. So yeah, just oof, yeah.
I think it was
I hope they come up with some kind of fix for this.
I think it was John Strand who said that Active Directory is just a 30-year long CTF.
Yeah,
and I feel like that's about right.
Yeah.
Speaking of Active Directory, we have yet another one, and this is so we got an alert from the Microsoft Threat Intelligence Center this week about Nobelium. Or Nobelium. I don't know if it's a short E or a long E, but this is the group that was behind the SolarWinds supply chain attack back in December of 2020, right?
Yep.
Was when that broke. And they are, so MSTIC has reported a lot of activity. It was actually super vague, that this group is now going after ADFS servers and using custom DLL path hijacking to create backdoors in ADFS servers to exfiltrate data.
Yeah.
So you want to talk a little bit about what ADFS is?
I'm not super sure actually about the details of ADFS. I do know a whole lot about DLL order hijacking though.
All right, well then let's flip it. I'll talk about ADFS. You can talk about DLL hijacking.
So DLL hijacking, this is actually something, if you're a red team or if you put this into your wheelhouse, you'll have, you got legs for days when it comes to getting payloads on target and getting them to execute. So the idea is that in a, let's say like a Windows environment, there's an application that is starting up, and when applications start up, they kind of look to other areas of the operating system to pull in different functionality, right? So in dynamic linked libraries, DLLs, there might be a function over here. So like the program says, okay, I just need that function and I need this one. And to do that, they need to know where these DLLs are. So when a program starts up, it will take a specific path to search for these DLLs one by one by one. The first thing that it looks for is in the current working directory of the application, and it says, is the DLL that I need in here? No, it is not in most cases. Sometimes it is, sometimes it isn't. Okay, let's look at system32. Is the DLL there? It might be at that point, but it kind of keeps going down that path, right? So in custom applications, there might be software engineering doesn't always go according to plan. Maybe they wrote something to look for a DLL and import a function that's not even there anymore. So DLL order hijacking is you as the attacker take a look at this application, you look at the internals when it starts up, and you pinpoint, okay, it picks that DLL right there, and it imports these functions from that DLL. And all I need to do is make a malicious DLL and just like Indiana Jones in the beginning of that movie. Basically, you got the golden idol right there, and you take the bag of sand, you kind of weigh it out a little bit, and then whoosh, like that, right? You just swap it right out. But you remember what happened in Indiana Jones when he did that. The boulder starts rolling down. So DLL order hijacking can be incredibly. It can inject a lot of instability into the program because the program's saying, okay, I'm looking for abc123.dll and I'm looking for these functions. Oh, here's my DLL. It'll load in your malicious DLL and then it might crash because you didn't tell it to like handle, okay, run my payload, but then handle all of the other stuff that happens after that. So it's a little tricky, but it's a really powerful technique because I gotta just between us people in chat and everything, I gotta give you a little insight here. DLLs are not scrutinized to the level that executables and even like PowerShell scripts and VB scripts, they're not scrutinized that hard because there are so many of them and they're so dynamic and they're all over the place.
Yep.
And there is a thing called DLL whitelisting, which means that you have a known good list of DLLs that are allowed in the environment, but implementing that from a practical standpoint is basically impossible.
Yeah, it's not possible. It's not possible.
So hard. It's such a cost overhead. So basically, people just say, all right, we're going to let DLLs be DLLs, whatever they are. So if you can find a good DLL hijack, it is like you land your malicious DLL, you've got to architect it so that it, or engineer it rather, so that it will handle kind of run my payload and then move on and gracefully go back into the process. But man, if you can pull that off, it's a phenomenal. It's like it's like APT level to be able to pull that stuff off.
In fact, it was. Speaking about the Nobilium group, DLLs were how they actually infiltrated the SolarWinds build process in the first place. What they were actually injecting their supply chain attack code into was a library, a dynamic link library that the SolarWinds Orion platform was using for their update mechanism. And so even at the build stage, this stuff is not always scrutinized as much as it should be. But then certainly once it's deployed, logging for DLLs, as Husky was saying, is super, super complicated because every single program on a Windows machine, when it starts up, it is loading a pile of DLLs and writing detective rules to look for ones that are weird is extraordinarily difficult and very
tough,
finicky.
man. Yeah, that's very tough.
And that's assuming you have the logging to catch those DLL loads in the first place, which is not a guarantee. Pivoting over to 80. Go ahead.
And I was going to say, we're actually going to see some DLL, some like the granular stuff of how DLLs load in action when we start to do the RE portion of the stream. So we'll, stay tuned for that. That's going to be really cool. You'll get to see kind of under a microscope what this stuff looks like. So yeah. But ADFS.
Yeah. So pivoting to ADFS. So let's say you are writing some applications for your business, for your organization, and you don't want to maintain a separate username password database. Great idea. But let's also say that you want it's an internal application. You don't want to have to use like Google or GitHub authentication or anything else like that. Also fine. So you want to tie your authentication to your application to your Active Directory database of usernames and passwords. Rad. How are you going to do that? You're going to use Active Directory Federated Services, or ADFS. And so what ADFS does is it is an ingestion point for authentication requests from things like web applications. So you write that integration with ADFS. The ADFS server takes that and then kicks off the traditional Kerberos authentication process for that username password, and then goes and does the whole thing, right? Make sure that you have, and so you'll see, if you're looking at your logging for this, you'll see traditional 4624 for successful login and 4625 for fails, but you can also maybe see ADFS logging for failures if you're looking carefully at the ADFS servers. That's event 411 actually. Um, Although it's not as detailed as it should be, and that's actually the problem here. So here's the deal: if an ADFS server, which often is exposed to the internet because bad network segmentation, right? Because if you are publishing this thing to the universe, and you're doing Active Directory authentication, and you are not using multi-factor authentication, so already we're two strikes in, if not seven, but definitely two. Um, if that server gets compromised, and remember, these can often be things like ASP applications, so there's a lot of attack surface.
Mhm.
Um, if those servers are compromised and this DLL is injected, now you are collecting all of those usernames and passwords that are coming in for
Yeah.
that for
Okay.
those authentication attempts. And
Wow.
then because this thing has privileged access internally, remember this thing has to talk to domain controllers, right? Even if it's like even if it's a duplicate DC, right? Not your primary, it still has to talk to a DC somewhere. And so now you have a pivot point to get inside the network and exfiltrate data out.
Yep.
And we know this thing has outbound to the internet as well. So it's a really, really concerning attack path. And so the back door that Nobilium is installing is called Foggy Web. And so the notification from Microsoft was like, look for bad stuff on your ADFS servers, to which my response is, cool, can you give us better logging for ADFS? And no, not yet, but it's something to be aware of. So for those of you who are using ADFS, definitely maybe throw some extra defenses on there, maybe higher levels of scrutiny for the logging coming
Yeah.
off of ADFS. Uh, ZeroX Muffin, thank you so much for the follow. Uh, so Husky, anything else to add on this story?
Yeah, ASP web apps generally very dangerous, lots of attack surface, just because of their integration with the .NET language, the .NET runtime. So that can always be a little tenuous, and if you throw Active Directory links in there as well, oof. I mean, and like you said, if it's tied to Active Directory, that's a pivot point not only for siphoning data, but also for if you have privileged access to the domain at that point. I mean, you can do credential stealing, you can do all the other kind of Active Directory shenaniganery that comes along with that. So it gets to the point where you have like web app permitted access to the .NET runtime to be able to tap into Active Directory. It's just like it's oof, man, that's a nightmare.
Yeah.
Um, yeah,
In terms of
sheesh.
in terms of defending against this, like what do you do? I hate to say this, but like the best thing to do is not expose ADFS.
Hmm.
You might want to consider putting your Active Directory tied um, applications behind something like Okta, where you are using that layer, which is not on-prem anyway, right? But it can tie in. But Okta is kind of handling that authentication portal for you. And also you can protect that after that with MFA. So I think even though that costs a little bit of money, it's well worth the investment to add that layer of protection, and not for nothing, but logging, because Okta has really, really solid logging for its authentication attempts. We have a question from OreoBite. What books are useful for creating Windows service or other binaries in NIM Golang? I don't know of any
Bucks.
because
Ooh. Mm.
NIM is super new. Um,
Yeah.
and I think
Well,
that the
yeah.
offensive stuff is, we're just starting to play around with it, right?
Yeah, we're on the forefront right now. Yeah, I have not built a Windows service binary in NIM at this point. Um, so I don't know. I don't think I can answer that,
A hacker
unfortunately.
says NIM in action. And then in terms of
Oh,
Golang,
sweet.
um, I'm not super. I have to admit, Go is not. I came to a crossroads, and I had to choose between Go and Rust in terms of what I was going to focus on in my programming, and I chose Rust. So I'm not super familiar with what's available for Go. I would check No Starch Press to see what they have going on. That's usually my first place to check. There may be some like because I know they have like Python for hacker books there may be a Golang book, and if there isn't one, I seem to recall that there's one in production. So Black Hat Go, there you go. Thank you, a hacker. So these
Sweet.
exist. That might be a place to check out. All right. So with that, oh, Ginger Root is on it with the link. Thank you so much.
Nice.
All right, so with that, I think we're ready to move on to the main material today,
All
and we
right.
are doing some malware analysis.
Yeah.
So let's head over to our Flare VM here, and let's
hmm
talk a little bit about what we're doing.
So, yeah, malware analysis. So I want to kind of set the stage. Um, so it's like 2019. I'm getting into a little bit more of the technical stuff in cybersecurity. Um, not OSCP at this point. I haven't really done many other courses and stuff. But this idea of malware reverse engineering is something that I caught hold of. And I started asking around and I was like, oh, reverse engineering, that sounds so cool. How do I do that? And at VetSec, which was Slack that I was in at the time, um, some of the members who do that professionally were like, oh yeah, check this out. Here's some resources. Here's some other stuff. And I took a look at the resources and I'm just like paralyzed. I'm like, this is all complete alien language to me. I don't know
Mm-hmm.
what's going on at all. Um, so what I wanted to do is take this idea of malware reverse engineering and kind of build introductory level courseware for somebody that was in my or is currently in the shoes that I was in a couple years ago. And the idea is that yes, the very deep, very technical parts like dealing with the like assembly language and that kind of stuff, decompiling and debugging, that's very, very important. But there is a place you can start with this stuff. And what I want to do is get you, if you have never picked up a piece of malware before in your life, if you've never like run malware in a lab, if you're not sure how to even start to build a lab to do that, I wanted to make a course for people that are in that position, and then get them gradually as the course went on, get them into the point where they start to hit that learning curve of debugging, decompiling, assembly instructions, and do so from a very practical standpoint. So I have been taught in the past malware analysis and reverse engineering that was very theoretical. What I wanted to do is get back towards what I see on the front lines as a red teamer and what I saw on the front lines as a blue teamer back in the day. And that is, let's do a heavy focus on Windows operating system, portable executables, PowerShell scripts, VBS, the stuff that is hitting the endpoints day after day
Mm-hmm.
after day that leads to ransomware infections and data exfiltration and that kind of stuff. So what I want to do is there's a whole bunch of people out there that want to do this stuff and want to become blue teamers but don't really know where to start. I want them to arm up with knowledge at this, and that's why I'm putting this course together. It's called Practical Malware Analysis and Triage, PMAT. I'm aiming at this point for an October release date. So the end of October, I'm gonna try to get it out, and it's gonna be available on TCM Academy. So stay tuned for that. But course aside, let's talk a little bit through the methodology of what we want to do here. When we are, and this is from like a philosophical, we'll start with like the philosophical level stuff. We'll get into kind of the what headspace you should be in as a malware analyst, triager, and reverse engineer. And then we'll start to get into the light technical stuff, the basic technical stuff, and then we'll do a little bit of the advanced technical stuff on this stream. So,
As someone who is very much in this same position of trying to learn all this, um, and I have found in my own journey into infosec that there is a specific class of material that is uniquely difficult to find good instructional content around, and it's basically anything that touches assembly.
yeah.
Um, uh, whether
And
that is
so you go ahead. Go
I
ahead.
was going to say whether that's binary exploitation, whether
Mhm.
that is reverse engineering, whether that is any kind of or malware analysis. It is there seems to be a whole bunch of just gaps in the
Mhm.
material. Either there are a lot of pre-assumptions about what people are going into with that information, or it's super basic. And then, much like a lot of other tutorial things, it's like, okay, well, I learned how to do that, but now what?
Yep.
So I just wanted to express my appreciation for a course that kind of is a little bit more holistic like that and considers the whole scope of the
Yep.
knowledge that is required to understand this material.
Yep. Um, the and there is a whole area of this. First of all, the first thing I want to say is that people make their entire careers out of being malware reverse engineers at the assembly level. So this stuff is, it's like the you're a martial artist and you probably have an appreciation of this, but like the simple things to learn can be the most like difficult things to master, right?
Absolutely.
So like assembly, the interesting thing about assembly is that the Lego pieces, I want to say, like the individual pieces are very, very few. For
Hmm.
x86 and x64 assembly on the Windows operating system, the pieces to put together are there are very few of them. And when you look at it, what they do is exactly what they do. Unlike higher level languages, there's no kind of abstraction to hide behind. It is straight up move this into this, call this, do this. It's so simple in like a conceptual from a conceptual perspective, but the way that it is unraveled and the way that it actually ends up looking is very, very complex, and you can spend a very long time thinking deeply about these simple things and how they interact. um, so if you want to get into reverse engineering and you're paralyzed by the idea of needing to learn assembly, what I would say is that there is a space for you to be an analyst, triager, and reverse engineer that you can be even if you don't know like assembly front to back to back to front, right?
Yeah.
There is a place that you can be in the field that's not going to require you to know that like 100% all the time, right? And the other thing that I want to say is that well, I actually lost my train of thought, but in any case,
Well,
yeah,
let me pick it up for you a little bit. So
yeah, sure.
it is also possible to descend in the stack
Hmm.
successfully. So,
Hmm.
my own programming journey, right? I started learning Python. That was my first language. It's about as high level as it gets. Um, Embarrassingly, the second language I learned was PHP because that was what I had available to me at the time, right? And so even higher
Yep.
level, right? In the
Yep.
web. Then JavaScript. I didn't really start doing systems programming at all until I started learning Rust, which let me tell you, as an introduction to systems programming, whew, but
Yeah. It's like
I
it's
ended
like
up avoiding C. And the
mhm,
point I'm trying to make is that I always knew that I wanted to eventually get down to understanding assembly.
mhm.
And it is super possible to get there in time. And I think that there are multiple roads to take there. Um,
Yep.
and there is no, I mean, there are, I guess, like assembly tutorials, like how to write Hello World in assembly, but that may not be the best way to understand assembly for
Yep.
the purpose of malware analysis.
Yes, exactly. So yeah, so when you're all right, let's talk a little bit about like the role that you take on. So we're gonna like, kind of role play today, right? We're basically taking on the role of a malware analyst slash triager that's been handed a little bit of information about maybe a binary that's come off of the endpoint, and we need to do some analysis on it to determine what it's doing. Right off the bat, malware RE and triage and incident response should not really be conflated. They're two kind of separate disciplines, right?
Absolutely.
Malware RE isn't really tied into the direct incident response phase of any kind of blue team operations, but it can greatly inform the incident response team and the incident response methodology, because what will happen is alert in the SOC goes off, weird executable spawning some weird child processes, doing weird things, calling to weird domains. IR will get there and like and roll out the kit and like and section off the network and like start asking questions and figuring things out. And meanwhile, they'll take that sample and send it over to the malware shop, right? The RE shop. And so we're not so much on the front lines when we're doing malware analysis. We're in the lab. We're like scientists, and I like to say that we have an alien on the operating table.
Yeah.
So when you think about the philosophical differences between engineering and reverse engineering, engineering is that you start with a blueprint and you know every detail about the bridge that you're putting up, right? You know every strut, every angle, every all of the physics associated with putting a bridge into, building a bridge and putting it into existence. Reverse engineering is the other side of the coin. We've got an unknown thing in front of us, and we have to use inductive and deductive reasoning to figure out what it's doing, right? So there is a shift of mentality here when we have something that we know nothing about, and that's why I say it's an alien on an operating table. Um, we're going to be doing is poking and prodding at the alien and looking at its antenna and its eyes and its limbs and saying, okay, but under what circumstances can I make something do this? Under what circumstances does the binary do this? Um, and so what we really need to do is look at the big picture in terms of what is this malware designed to do? What can I make it do? And what's it constructed out of? And that kind of thing. So it's just it's a very different take on when you're building malware. And I've been writing the malware for the course that I've been putting together. When you're building malware, when you're engineering it, you have all the answers right in front of you. You just need to put them into practice. We need to go track down the answers for this one.
Yeah.
So to start out,
sorry, one other
yeah,
point I wanted to put up there is that you talked a little bit about the difference between incident response and analysis, and just a couple of like real world practicalities. First of all, if you have a malware analyst on your blue team, you are a special snowflake. That is usually not what's going on in most places. And we're already assuming that your organization has a dedicated a CSIRT, cybersecurity incident response team. Like that's not true everywhere. Maybe not even in most places. But if you do, this is a damage control team. Their job is to stop the problem, right? It's not to get too graphic, but if you have a gunshot victim on the table, your job is to stop to heal the wound, not to analyze the bullet. That happens later, and that's kind of what we're a difference in time span as well, because during incident response, like you want to make sure that you stop the problem, and you need to understand the malware enough to like know what you're looking at and how far the infection has spread, things like that. But really getting into the nitty-gritty, oh, this is interesting, like and figuring it out for attribution and things like that, the deeper investigation, it's on a much different time scale than initial incident response.
Yep. And so what I want to present to either the blue teamers that are watching this that are saying, why should I maybe pick up if I'm a SOC analyst, if I'm IR, why should I kind of pick up these skills? And the red teamers watching this and the penetration testers saying, this doesn't concern me. Why should I pick up these skills? There's area in both of those two disciplines to apply the skills that I'm trying to teach in this course. As a blue teamer, if you're IR or a SOC analyst, any amount of malware triage skills that you can apply immediately when you see something that doesn't quite look right is going to be super, super valuable in the, like, as soon as something drops onto an endpoint, like time is limited. Like time, you're on the clock at that point. So, you can apply the skills there. And then from the other side of that, speaking as a professional red teamer, zero things have improved my tradecraft and ability to perform red team operations more than studying malware. Like, no cert on earth, no class that I've ever taken has taught me more about what these things do and how they evade detections and how they operate, more than like crawling the web for malware, sourcing it, and ripping it apart and taking a look at the different functions and how it works. So it's got applicability in both of the disciplines, and I feel like I know, Taggart, I know you know this. We're losing the fight against big evil cybersecurity forces out there.
Yeah.
And we've got to arm up. We need to arm up with more knowledge about how to respond to this stuff, how to reverse engineer, and how to really report it, so that the last part of the course is rule writing. Like the very, very end, the final part of this course is like write rules, publish, and tell the world what you saw. And that's what we need to do more of. So
absolutely.
So what do you say we get into it, man?
Let's do it. Let's do it.
Let's take a look. Okay. So with kind of the philosophical stuff out of the way, our general methodology as analysts, the first thing we want to do is handle malware safely, right? So what you see on the screen right now is just the setup here. We've got a little note from the IR team, and it says, we've pulled this off the endpoint. We need to do some analysis. It's just a little bit of role playing, a little bit of setup. So let's think about malware handling. So if we have a specimen that we have collected off of an endpoint, what do you think is something we don't want to have happen? Especially if you consider transferring it to other hosts and taking it and sending it to your malware analysis team. Like, what's the one thing we want to prevent from happening after we know that it's detonated or the malware has infected one host?
Yeah, I want it to stay, this is outbreak control.
Yep. So
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 we want to
you
keep
need
it
this thing. Yeah, you
isolated.
need this thing to be inert. Yeah, you want to defang the malware, right?
Hmm.
So on a window, the course focuses a lot on Windows portable executables and Windows scripts because that's the big attack surface, right? On a Windows operating system, you can change the metadata of a file without changing the contents of the file itself. And you can change the metadata of a file without changing like the file hash or any of the other kind of identifying features. So one of the first things that we want to do if we find a sample, we want to defang. And so we can do this. We can do this one of two ways. We can do this like manual to show kind of the methodology, or we can break out Blue Jupyter and show the notebook that we built for this. But effectively, what we want to do is run this through an initial stage of triage where we control that we have positive control of the malware. We defang it so that it won't run unless we absolutely intend it to, and we transfer it to a safe location, which is usually a password protected zip file with a standard password of infected. You'll see you'll see malware, you'll see some other word, but usually it's infected. And the idea is that we are going to handle this safely. And I'm reminded of back in combat training at Marine Combat Training School. My instructor at one point held one of the dummy grenades in his hand, giving a presentation for one of the classes on what we were going to go do out in the grenade range. And he removed the pin and just held it for the whole talk, right? And so he was basically like, these things can't hurt you if you handle them correctly. All right. So we need to teach you how to handle them correctly. Same kind of things going on here. Malware can't hurt you if you handle it correctly. And the times that you're most vulnerable are when the malware is in transit to where you need to put it into the lab or moving it off of the endpoint or something like that. So, with that having been said, one of the most effective ways that I've ever found to defang malware is to change the file extension.
Hmm.
It's very, very, very easy, super, super simple. So let's go ahead and open up our the sample. We've got unknown exe.mals.
So to let me back this up quickly, so
Yeah, sure.
that what came to me from Husky, right? And actually, let me back this up even further. So let me explain where we are right now in the process. So,
Mm-hmm.
um, we have the sample; it has been captured, and I have it in my lab machine. The lab machine is configured. It's using Flare VM, which is from FireEye. It's just kind of actually, it's a script that you run on any Windows machine, and it will transform it into a
Mm-hmm.
malware analysis laboratory.
Yep.
However, that's just about software that gets installed. The next thing that I have to do is, and I have this in Hyper-V here, the next thing that I do is with my Flare machine, I create a checkpoint.
Mm-hmm.
Okay.
Huge.
So
Huge.
what am I doing with the checkpoint? I'm saving my game, right? I am
Yep.
saving the state of my machine before I try to run anything evil on it so that I can go back in time to before I've done something evil, in case something goes awry. And in fact, we're intending for something to go awry here. That's
Yep.
one. The other part of this that is super, super important, cannot stress this enough, is, oh wait, I shouldn't have double clicked on that. Let me get back to the window. Yeah. So the other thing that I can't stress enough is you have to make sure that you are disabling
Yep.
your network connections on this thing. So I have different network adapters, right, for my Flare machine. This one is the default, which is connected to the internet.
Mm-hmm.
And then I have the isolation lab device that is connected to just a completely isolated lab environment. There's no network connection.
Yep.
So what I want to do with this is make sure that there is no internet connection whatsoever
Good.
to this
Very good.
machine, right? So I'm going to
Excellent.
hit apply for that. This thing is totally isolated, barring a VM escape or something like that, but it is totally isolated.
Yeah. A word about VM escape. I get this question all the time. Like, what about VM escapes? They technically do exist. They are so rare that it is. I like to, from a risk analysis perspective, because all of this is risk analysis, right? All of this is, and this is risky by nature. This process is risky by nature. From a risk analysis perspective, a VM escape in any random sample of malware that you find is akin to a meteor strike. It's like, yes, it is technically possible, but like, it's just so rare, and the conditions need to be so specific for that to happen. And I'd never say it's impossible because obviously it's happened before. There are proofs of concept out there. But for any regular analyst to grab a piece of malware and have it do a VM escape is just exceedingly rare. So I wouldn't so much worry about that. But there are still other ways that you can hedge against that. But yes, Taggart, you've nailed it. You've nailed the setup. We need to do this safely. We need to do this scientifically. So yeah, backups serve two functions. It serves, the primary function is that when you run a piece of malware, it will have destructive actions, activities on the system. But it also might do things like install itself as persistent.
Mm-hmm.
It might write itself to the startup file. It might write itself to a Hive key in the registry. And you don't know any of that. At first detonation, it might do a whole ton of things that you don't know because there's nothing to see from the naked eye, right? So we need to be scientific about it. We need to control for all of our variables and detonate the malware, make observations, and then run the tape back, and then bring it right back to where we were, detonate it again, make more observations, run the tape back. And every time you do another detonation, you're using different kind of tools and stuff that you can kind of approach it from different angles. But yeah, the other part is that we can simulate to a certain extent the outer world inside of a malware analysis lab. We don't need to connect this thing to the internet, and it's very unsafe to do so. And so removing your internet capabilities from your lab machine is highly recommended, if almost not requisite to do this kind of work.
I will say there are some labs that do connect their lab machines to the internet. I mean, and at this point, we're talking about like Project Zero.
Yep.
And like the higher level malware analysis labs are like the actual research firms, like Unit 42 at Palo Alto, like the actual pros. Here's why: they need to see what's going on from the attacker's network architecture, their network infrastructure, to see what's going on. To do that, they will have almost certainly a dedicated internet connection for their lab machines that is totally isolated physically from the rest of their network.
Yeah, think like Citadel level security on a point of presence on a network. Like nothing else goes in or out of that. Let them do the heavy lifting with that. And they will discern lots of important information about attackers' infrastructure, but we're not so much concerned about that. We can still get a lot of information emulating and faking internet and having the binary think that it's talking to a resource that it's calling out to, but not actually doing that. We can get tons of information and we reduce the risk associated with that. So let those big malware RE shops handle all of the heavy lifting when it comes to actually being connected to the internet. And we will use our crafty, scientific methods to make the binary think that it's connecting to the internet when it's not. So we have our binary here. We've got it password protected in unknown.exe.7zip. Generally, when I like to save my specimens, I'll throw a prefix and a suffix to them. The prefix is usually the type of malware that I like to do. If you don't know it at that point, I usually just do malware. Unknown.exe is the original extension. So if you just get a piece of malware, if it's just a file name, you may not know how to run that until you start to look at the internals of the file. I like to just throw the extension on there just to say, hey, if you want to run this, this is the actual extension. And then the suffix of this, you see 7-zip here because it's in a zip file, but the suffix could also be the defanged extension. So why don't you take unknown.exe and let's defang. You can call it defanged. I use MALZ just so that I know that it's malwares like that.
Yeah.
You can also throw the type of malware on the front end like that. So you can do either malware. We don't know what this is yet, right? We're going into this blind. Generic. Awesome.
That's
Perfect.
what you'll see very often from actual malware reports.
Now, why don't you go ahead and double click that? Windows can't open this type of file. All right, fantastic. So what does that mean? We need to now tell Windows how to run this file. And that's actually super important because if we are moving this thing around and we drop it to like our physical host, God forbid you take an exe alive, like armed exe and transfer it by dropping it from the target onto your physical host. And then let's say you get a little too excited and you hit enter and it runs, you've now infected yourself with malware.
Mm-hmm.
Ouch, big ouch. And that's your physical host. That could be ransomware. That could be anything.
This is the malware analysis equivalent of trigger discipline.
Yes, exactly. This is keep your weapon on safe until you intend to shoot.
Hmm.
This is keep your malware on safe until you intend to detonate. I'm writing that in the safety guide that I'm writing for this. I basically take the four weapon safety rules and I say to iterate on those. We follow similar disciplines here. So at this point, if you double click on that, it'll ask you how you want to run it. I think if you actually open up command.exe and invoke it from command.exe, it'll do the right thing. It'll actually execute it. But now we don't have to worry about firing the M16 without us intending to, right? Like
Hmm.
this is now defanged and we can move it around for our operating systems. Let's break out Blue Jupiter at this point.
Ooh,
And this is a new project. You guys are seeing kind of the new hotness in chat right now.
that's true.
This is kind of a new project that Taggart and I have been putting together. And Taggart came up with the idea for Jupyter notebooks for blue team purposes. And I was like, "Ooh, I got the malware analysis one. Awesome." So what we have is, and actually we can move it in as unknown.exe because it will defang it as part of the
Oh, that's right.
as part of
That's
the
right.
notebook,
That's
right?
right. So let me
So
move that
so
back.
yeah. So the idea is that this is a Jupyter Labs notebook that you can bring malware samples into, and it'll do a lot of the kind of like what I call tedious, but is very important, like prior work before you set stuff up, right? So we've got it in the Dropbox. All you need to do, you can go to GitHub right now actually and find this.
Yep, I just
Yeah,
put
and,
the
and Taggart
repo in
just
chat.
posted it. So you can stand this up as a Jupyter notebook. The instructions are in there. All you've got to do is install the poetry dependencies. And so what this is going to do, let's fire this up and go to. We'll run through starting at the first cell, a bunch of imports, and we will enumerate to see what we have in the Dropbox
So
and just make
yeah,
sure that the
let's walk
Dropbox
it through. So
exists.
so
Yep.
what Husky provides in this section of the notebook, right, is this folder called Dropbox, and anything you put in there is going to get analyzed. So we have moved. There are three things in Dropbox. There's unknown.exe, and then there's a sample negative.txt and sample positive. And Husky, what is the positive have the icar string or something like that?
Positive is the
Okay,
iCar stream. Negative is lorem ipsum,
nice.
effectively. Or maybe
Okay,
I'll put Jeff Sum in there now that you
yes.
you show me what that is. So yeah, so the idea is that on a Linux box, you can drop an executable right to a Linux box, and given that you're not like using wine or cross compiling and cross running or anything like that, for the most part, that's effectively defanging a malware sample for Windows. For a portable Windows executable, having it on Linux is actually pretty safe. Like you can't
Yeah.
really invoke that as you could invoke the Windows operating system equivalent, right? Um,
Little off topic, but the way that Windows and Linux decide how to how to open files is slightly different.
mhm,
Um, and this doesn't for Xes it doesn't matter because they can't run portable executables really anyway, as you said, without Wine. Although some distributions do actually make a MIME type connection for .exe to
mhm,
Wine, which is a bad idea, I think, but
yeah,
whatever. Um, but yeah, so totally safe. Destroy Worlds asks, is this OS specific? No. All of the stuff that the Blue Jupyter notebooks use is they're just Python modules, and
exactly.
so
Yep.
you can run it as long as you have the Python dependencies installed. You can run it on either or on any OS. And I put it in Linux just because I am comfortable with that. But if I had set up Jupyter to run in Windows, it would work exactly the same way.
All right, so let's keep rolling here. We will enumerate the samples in the Dropbox, and if we hit go on this cell, we've got Dropbox exists. If they don't exist, it sets it up for you,
Hmm.
just as kind of like a handling thing. And we're going to enumerate samples in the Dropbox.
Okay, it found unknown.exe.
Fantastic. Okay. We're going to instantiate objects for the Python backend of malware samples.py, which is in there. A lot of kind of abstracted stuff. You don't really need to worry about that. But basically, I wanted to have like an object for each of the samples to be able to keep track of the what do you call it, like the attributes, right?
Hmm.
So we'll instantiate the objects, and then we're going to defang and save these to the save specimens directory, which is we'll slice or we'll not slice anything. We'll just add in the prefix and the suffix. So if you go into save specimens at this point, you should have
I have three
um,
folders.
yep, sample negative, sample positive, and is that the timestamp from right now?
Yes, it
10
is.
02 21 10 4. Okay. So yeah, see how it's malware.unknown.exe.mals. We have defanged our sample. We've appended it with the type of malware, which we don't know anything about it, so we'll just call it malware. Taggart called it generic. It's really up to you, and you can. I mean, I could maybe even add it in so that you could specify what type of malware it is. But let's start. One of the most important things that we can do is take the fingerprint SHA-256 sum,
Mm-hmm.
and we'll go ahead and run that cell, and it should give us the. Did I not? Oh, you know what? I think I had it print out. That's okay.
No,
I
that's
wouldn't.
okay.
Yeah,
So what
we
we're gonna do is
yeah
we're
we
gonna
can
do
just
obj
let's just
dot
print it out.
SHA-256 sum, because what he's doing, right? If you look at the code, he's adding this value to the property, right? So
So
SHA-256
just print it right
sum,
out,
um,
and we'll
do,
have
do, do,
we
do,
have a
do.
few objects in here, so you could even do like a for object
That's exactly what
in
I'm doing.
sample
For
objects. Yeah.
O in sample opt, right? Is the
Yeah, that should do it. Sample
is
underscore
the
obj.
list.
Yep. And then
Boom.
yeah, nice. Okay, so the third one should be, and you could even do like print object name and then sample. But so the SHA-256 sum, this is great because it's like a fingerprint. So if you submit this, which we'll do in a little bit, submit it to a virus database, they may be able to identify it with the fingerprint. There is a slight problem here, and there's something that I want to implement in a further version of Blue Jupyter. Okay, malware authors know that people fingerprint their files, so they change them a little
Mm-hmm.
bit. What I want to do is implement SSDeep, which is a fuzzy hashing algorithm. And so hashing goes block by block inside of a file. And so, like, if you change one thing, one tiny little, a comma even, the hash is going to be completely different. But the fuzzy hashing algorithm will look at the homologies of those blocks and say, okay, 9 out of the 10 blocks of this hash look exactly the same, and this one block is different. So we can say with reasonable confidence that this is a derived hash of the original sample, right?
Yep.
It's just a little bit has been changed. The SSDeep library can do that. I'm still working on implementing that, but that's a future state thing.
That's very similar to what a lot of next gen antivirus does,
Yep.
which is if they're given a binary, the antivirus program will know, okay, well, an executable has different sections in it, right? It'll have a section where kind of the preamble is, where text
Mhm.
stuff is stored, and what it will do is will actually hash those different sections of the binary, because changing like the ASCII art or changing the comments of the source code for things like that won't change the whole thing.
Mhm.
So by combine, if it like 4 out of 5 of the section hashes match, you're still going to get a detection.
Mhm.
So very, very similar process.
Yep. So we're moving on. The next part of this is to pull the strings out of the binary. Uh, Now, Taggart, what is a string?
Ooh, so a string is the way that we think about it as humans is essentially the way that computers handle text. But a
Very good.
string in actual implementation, right, is that every single one of these letters you see in these quotes, this is a string. But what is it? It's really a sequence of smaller data types, which could either be called characters, but the characters are representations of special numbers, right?
Mhm.
And those numbers, depending on what kind of encoding you're using, are represented with either 8 bits or 16, and they correspond to characters that humans can read. So
Very good.
okay, I'll stop there.
Yeah, so a string. So if you've taken CS50, Harvard's computer science intro course, Professor Malin says, I think I've tricked you all because we started this course saying that there is such a thing as a string. There's no such thing as a string. What does he mean by that? A string is a kind of data type, but a string is really just a set of characters in an array. So it puts a bunch of characters into a block where they all have position in the array, and it says, okay, character 1 or character 0, 1, 2, 3, 4, and then usually a C string will terminate that sequence with a null byte to say that is the full string. So the answer that Taggart gave is fantastic. From a computer science perspective, a string is like a set of individual characters that form a kind of different data type. But to a human, a string is a word, a sentence, a phrase. It can be any number of things. It can be an address. Computers don't get what words are. They don't know what phrases are, but they do know what strings are. And so inside of a portable executable, when you think about what a portable executable actually is, like what it is at a kind of fundamental sense, when you open up like a PowerShell script, you know what it is. It looks like a bunch of text, right, in a file, right? Those are easy to think about what they look like. A portable executable is not really that easy to understand until you look at kind of the bytes associated with it. And all it is, a portable executable is a well-structured series of bytes that all have a specific function. The first part of the portable executable says, I am a portable executable. The second part says, I cannot be run in DOS mode. The third part says, I set up the locations, and so on and so forth. When you think about what a string is inside of that series, all it is a series of bytes that make up a word. And so strings can be super valuable to malware analysts because what could a string be? A URL. It could be a password. It could be a username. It could be a file directory. It could be a registry hive key. If you're a lazy malware author like me, it could be all of those things. So pulling the strings out is super important. There are 3 tools that I like to invoke to pull the strings out. One is strings, the strings utility itself. That will give you the plain Jane rip all the strings out of length 4 or greater. And
Sorry, I had to make this in real time.
oh man, that's so good. Yeah. So exactly, it's all
Everything is
just bytes.
just bytes.
When it comes down to it, it's all just bytes. So the strings utility will pull all of the strings of size of n4 or greater. The floss utility is the FireEye Labs obfuscated string splicer, I believe. Floss is like it's an improvement on strings. It will pull the strings and then it'll do some with some nice Python magic in the background. It'll slice up the strings. It'll say these look like Unicode characters. These look like ASCII strings, and it'll give you a little bit more enriched data. But what I implemented into Blue Jupyter is I think a step above that, which is String Sifter, also developed by the FireEye team. And it uses what I'm going to take their word for it that they're using a machine learning model, excuse me. And it ranks the binaries strings by malware analysis relevance, right? Does that make sense?
Yeah.
So I haven't looked at how they do this, but basically they pull the strings and they assign a score. I think out of like the higher ones are like 12, 13, 14 are like, yeah, this looks bad. The lower ones are like in the 0.0, 0.0 range.
So I can tell you a little bit about how they do that, which is
yeah, sure.
And this is true for a lot of malware analysis, right? Is that they are scoring entropy.
Okay.
So entropy, right, is there's the physics definition, which is like the amount of disorder in a system that prevents energy from actually being, released. But in terms of entropy, when we're analyzing a file, it is the amount of disorder, like the randomness against what you would expect inside of a file. And individual strings can contain higher levels of entropy. And so, for example, on Wednesday, when we were creating obfuscated shellcode, we were tossing tons of entropy into that file. So we were actually making ourselves noisier from that perspective, even if we were obfuscating the actual shellcode that we were trying to inject.
I put an ASCII art version of Jeff Bezos laughing at one point to throw some entropy into a payload that I put. All right. Anyway, so we're gonna invoke String Sifter, and we're going to pull the strings and rank them by score. So what we need to do is say desired minimum length. I recommend 8 is probably the one that I go for. Usually a string of 4 or less is not going to be very useful for your malware analysis efforts.
Can we run strings raw just to
let's run strings and show why that's a bad idea.
So we're gonna run strings against unknown.exe. And this is
I would I would do like a less here because it's going to be a lot of info.
Well, I'm in Tmux, so I can scroll back up, but
cool.
That's so.
And then, all right, some of this might be okay. Some of this might be good information. I see MingW right off the bat. So like I see cross compilation. I see new file system, alloc, valloc. I see some other stuff. But the higher you go in this binary, the worse this information is probably going to get for you.
Yep. And by the way, sorry, I just wanted to call out, like, what is strings doing? Because, like, if it's all bytes, what makes it a string? What strings is doing is it's looking through all the bytes and finding those byte sequences terminated by null bytes that contain exclusively printable characters. That's how it's distinguishing strings from not strings in the entire sequence of bytes that makes up the file.
but a principal character and a null byte does not a word or phrase make. And
Right.
the problem is that this binary is chock full to the brim of things that are principal characters and are terminated by null bytes but are completely useless from they serve some kind of function in the binary itself. Maybe it's a jump instruction, maybe it's an instruction to do something in the binary. But they're completely useless from like a word perspective. They're not going to tell you how this thing is calling out to URL. They're junk characters, right? Yeah, I
Mhm.
think you need to go like pretty high up in the thing, or just do a less, and you
Yeah,
should
let's do
get
that.
pretty close, like right up at the top.
Yep,
Yeah,
just
this is a very good.
nonsense.
So aside from the very first bytes in this portable executable, which are quite useful, this designates that it can't be run in DOS mode from the DOS header. It goes into the text section of the image file headers. Look at all the rest of this stuff. D $ open paren H. I don't know, man.
Mm,
That could be like an instruction.
Hmm,
That could be
a
something else.
clue.
Yeah. So if you run strings without a minimum strings argument, you're in for a world of hurt when it comes to trying to determine what this thing is actually doing. And that's why I recommend string length of 6 to 8 is probably going to be your best bet. It's still not going to be perfect,
Uh,
but
you can do
yeah, and
that
then
from the command line, by the way, if you do the
yeah,
dash
dash
n
n. Yep,
8,
exactly. And like any self-respecting
but it's
malware,
still.
any self-respecting malware tool that pulls strings is going to implement the dash n argument.
Hmm.
Floss does it, string sifter does it. So let's do of length 8 and just make sure. Yeah, I think you should be okay. Yeah, just make sure you hit enter there. Good. Okay. And then let's pull the strings here. Awesome. So we've got sample positive, sample negative, and then this one might take a second, but then boom, we've got our string sifter out.log. If we go into save specimens at this point, we can open up unknown and we go to string sifter out.log. And if we open that up, we now
Beautiful.
have our ranked by comma delimiter,
Oh, look at
ranked
that.
series by score. 10.21 is pretty bad. 9.9. See user public password.txt, huh? Okay, interesting. So this is what at the stage of malware analysis that we're in, we are standing over the alien on the operating table and we're kind of maybe poking a little bit. This is the basic static analysis section
Hmm.
where we are not running the binary static analysis and we're taking a quick triage limited approach to the tools that we're using. And basic static analysis is like us standing over the alien with a clipboard and kind of like looking at the antenna and saying, okay, I see some antenna, maybe that's transmitting data from its mothership or something like that, but I'm not totally sure at this point. This is all about taking little pieces of information and like doing the Charlie Day with the cork board and all the all the little red strings and stuff. We're gonna tack that piece of information right to the cork board, and we're gonna say, I don't know what this does yet, but that's super super juicy. See users public password.txt. I don't know what that does. I'm gonna put a pin in that and put it right up on the cork board, and we're gonna figure out what that's doing.
And
And
let me
so
call out
yeah,
that at this point, depending on how your investigation has initiated, you may not know that this thing is malicious. You may suspect that
good
it
point.
is,
Very good.
right?
Yeah, absolutely. So the more stuff that we can get out of the basic static analysis is going to inform the follow-on dynamic analysis, which is when we actually run this thing to see what it's actually doing at runtime. And so you can't. Strings are good. Strings are critical, but they cannot tell you what is going on with the binary until you actually put this thing in a sandbox and blow it up and see what happens. You're not going to know for sure. So,
As
but
a
let's
blue teamer, though, I will let me call out a couple of things that I'm
yeah,
seeing
go.
already.
What are you seeing? What looks good to you?
So, because I'm me, I know that this thing is written in nim because I'm seeing .nim all over the place, right? So,
I am a creature of habit. What can
right.
I say?
So I see that. That's the first thing, right? And I see the nimble packages, and I see Winim. So like because
Okay.
I have written nim malware with you, like I know that this is pretty sus, and that's why we've
Yeah.
got the
Yeah.
10.21. That's one thing. However, the HTTP client is also telling me that we're talking about something that makes HTTP calls.
Okay.
Um, and then actually later down here on line 13, I actually have a URL. Now, this is
Ooh.
cdn.altimeter.local. This is a .local, so we know that this is a lab environment. We're nice and safe. But if
Yeah.
I saw a URL inside of a inside of a sample, the
Oh
first
lord.
thing that I'm going to do is I'm going to take that URL and I'm going to go to a few different places. I'm going to go to Cisco Talos, I'm going
Hmm.
to go to Virus Total, and I'm
Yep.
going to go to Abuse IPDP and also maybe URLscan.io and just
Nice.
run that URL against those sources to see if anyone knows what's up with it. Then
Yep.
I will take the resolving IP address and send that IP address into those same tools as well as graynoise.io. Um,
Hmm.
and
Nice.
just to learn, like, what do we know already about this destination? Is this something that we know that bad actors are using?
Awesome. Nailed it across the board. That is, if you pull a URL out of a binary, if the malware author is lazy enough to not obfuscate a URL in a binary like that, and you pull it in the static analysis section, you've already got ammunition to go to put this thing on a block list. Go canvas virus total, go figure out if this is evil or not. Unfortunately, malware authors tend to use DNS records because they're easily burnable as opposed to IP addresses. So even if you see a URL in there, there's no guarantee that it's going to be the one that's going to be
Yep.
useful to you as a blue teamer. But you've got to try, right? Like it's you've got a piece of info. So what I want to stress is that note keeping in this whole process. Remember, we're scientists. Looking at an alien, we've got to start keeping our notes. We got to start building a case for what this thing might be doing. Excuse me. So we already, yeah. So let's answer some of the challenge questions. We know that this thing is written in NIM, unless there was some crazy, crazy obfuscation effort to make this thing look like a NIM binary when it wasn't. I
Yep.
didn't do that. I'll just give you that one right there. Yeah, we know this thing is written in NIM. Okay, we can't quite answer the other questions at this point,
Right.
and we don't even necessarily know the answer to what is the first callback domain.
No, we don't.
Um,
We
it's
found
because
a domain, but we have no
we have
guarantee
a
that's what it
domain,
is.
but we don't know if that's the callback domain. So let's go back to Blue Jupiter and let's see. Let's throw this thing into Virus Total. You do need to provide your API key,
Yep. Let me quick
which
copy
is
pasta that out of.
awesome.
I have it open because I knew we were going to do this.
Yeah.
And for those of you who are concerned about OPSEC, we do have some comfort. So GetPass, the library we're using specifically to do this, um, doesn't save the plain text version of your API key, but you know, just be aware of that. That we like to clear our outputs whenever we restart the notebook anyway.
Yep.
Okay.
And then it will just quickly assess if an API key was put in. That's okay. So just run through that one. And then we are going to, for every object that we have, we're going to throw in a SHA-256 sum. I see it's SHA-25 sum, so I got to correct that typo. So it's done. The positive and negative samples look like we've got good control
Mm-hmm.
over if a sample positive is going to return okay. But it looks like unknown.exe doesn't return at this point. Between you and I, when this course goes live, I expect that to change.
Yeah, I think that's
But
right.
that's okay. So let's zip up and password protect. So let's go ahead and hit that next cell there. And what we're doing now is saving this thing into a password protected zip directory so that we will have this as a stored specimen that we can return to.
Mm-hmm.
And it encrypts with AES 256 and with a password of infected.
Nice.
So again, if you want to throw this to your buddies over at the another RE shop, or maybe put this thing out on a GitHub repo to say this is a sample found in the wild, it's considered best practice to encrypt it, put a password on it, and just defang it really, so to keep it safe.
Or if you want to
Oh, Malware Bazaar, yeah, here we go.
Malware Bazaar,
Yeah,
you
I had
have
an idea for this too. If my idea for Blue Jupiter is that if you don't have any samples on hand, I'm going to call to the API key of or the API of Bazaar,
that's really
and
cool.
you can like window shop. You can be like, ooh, this one like give me the like 50 samples that have just rolled in. Like, ooh, this one looks cool, and then just pull it right off. So, and then debug variables for that. No need to run that one. But
Okay.
we have
Very cool.
triaged. We've done our static analysis, our basic static analysis at this portion. Let's head on over and blow some malware up.
So before we jump in to the dynamic analysis, there are a couple of other tools that I just wanted to shout out, if that's okay, that
Yeah,
I would
go
run
ahead.
against this tool, or against a sample. So one of them, let me extract my XE here. Oh no, I have a defanged. That's fine. I'll just
Yep, you have a defang.
right.
Yep.
So the first thing that I might use is something I deeply love called PE Studio.
Yes. Yeah.
Uh,
Shoot, we should have gone into this, but yeah,
okay,
no, please, do it up.
so what does PE Studio do? PE Studio is going to run some pretty standard checks, kind of like the notebook, but it has a. I think that there's different values in how our notebook works versus what PE Studio does. But PE Studio is going to look for certain patterns in specifically Windows executables, right?
Mhm.
Um, and see what's going on with those things. Now, this thing isn't connected to the internet, so it can't do the virus total check, but
Mhm.
everything else on here is going to execute. What is it looking for? It's going to be looking for suspicious patterns. PE Studio has built in kind of allow and block lists for the things that it's expecting to see in an executable and things that might be weird. And if it
Mhm.
finds any of those weird things, it's going to show it in this indicator section as it analyzes the binary.
Yep.
But even before that, it's going to give you the checksums, the MD5, the SHA-1, the SHA-256 right off the bat, and then anything else that it finds.
Yep.
Um, as it goes through, so we've done the full investigation. I know this is a little small. I'll turn on my magnifier here. Yeah, that's not the magnifier I wanted. I wanted this magnifier.
Of all the tools in the basic static analysis phase, this is my favorite one by a long shot.
Yeah.
It's the one I go to most of the time.
So, we have a question from OreoBite, by the way. What is the final exam going to look like for the course?
It's WannaCry.exe actually.
Oh,
Like
so
the
just call up
actual
Marcus and then you're good.
it's yeah exactly. No, Marcus is gonna sail through this court. No, it's the actual not defanged, not neutered, completely real WannaCry.exe. And the idea is that I introduce it early in the course and say this is what malware can do, and this is why it's so dangerous. And we're gonna come back to this later as kind of like a boss fight. And then that's the end of the course is to do a full investigation on that, including a limited amount of like advanced decompiling and debugging and stuff. So
Awesome.
yeah,
Awesome.
WannaCry. Maybe some other ones too if I have the time for it, but WannaCry is the big one.
So we see in our indicators here up at the top, we have these things in red, right? That the file references strings. Okay, well, what strings? If we go over to the strings section, it'll tell us, what are we looking at here? It's loading all
Yeah, it's
13,799 of them.
quite a lot. Yeah.
But up at the top, I think because I have them sorted by the things that are in the block list, not blacklist.
Yeah. Thank you for that because
Don't
I
worry.
need to get better at that. Yeah.
But so what is getting flagged here? We have connect, send, and select. So we're talking about basically networking terms. So this thing is making network connections, and that's a little bit concerning. So these are getting flagged here. These aren't
Or
smoking
is it?
guns really, but
Yeah, or is it, right? Spotify makes network connections. I mean,
right.
so who knows? But yeah, it's
PE
a
Studio is
potential
paranoid,
indicator.
but that's okay for
Yeah.
us. The
Yeah.
file contains another file. That's interesting. And then, did you do this on purpose? The file exposes thread local storage callbacks.
I'm gonna tell you just from like a white cell perspective that I did not do that. I couldn't figure out how to implement that in time. That's super interesting that it's picking up on that. Maybe the NIM compiler implements that like in some capacity.
That might be what
But
we're
no,
seeing
I
because remember we looked at the multi mains.
hmm
That might be
Yeah,
what that
it's
is.
possible. Yeah, I don't know. I need to do more research on that. I did not put any intentional TLS callbacks in there. If you're wondering what a TLS callback is in a very TLDR, it's thread local storage, and it basically means that before anything in the binary is invoked at runtime, you can actually run code first before any of that happens. Practically, what does that mean? If an analyst is doing debugging on it, if they attach immunity debugger right there, and the executable fires up, it'll run code before immunity debugger even gets the chance to load into the very first entry point of the binary. Super scary stuff. But I'm not good enough yet to actually implement that. So
Now, this is something interesting that I learned when I was running PE Studio against this sample earlier, which is that when you compile this thing, uh, and you have WinIm as the library you're using, that becomes the manifest
mhm.
name. So
Sweet. Okay.
that can be an indicator for
Nice.
detection if your attacker doesn't know how to change this up in the
Yep.
assembly identity. But yeah, so no real smoking guns off of PE Studio, but it's something that I like to run. Would it run if you load up for reverse engineering? If we loaded it into something like Immunity and hit run, yeah, it
Mhm.
would.
Yeah,
The
and I think we'd have to change it back to executable. Maybe I'm not totally sure about that. You'd have to rearm it, I guess. But I guess we can check that to see.
Yeah, the
But
other
yes, it. Yeah, go ahead.
I was just gonna say the other tool that I like to fire off against these things, just because Cutter is going to have more information than you need at this stage. By
Oh, Destroy World said the TLS part. Yes, if you load that
yeah,
into a debugger, that code will run before the debugger has a chance to get to the entry point, which is super scary if you think about it.
definitely.
Sorry for interrupting,
No, no,
but
no,
yeah.
absolutely. So what I like about Cutter, even if I don't want to load up the entirety of the disassembly, like I can look at it if I want, but I don't have to.
Mhm.
First of all, it gives me a bunch of information in this overview. What kind of a thing is it? It's a 64-bit executable.
Mhm.
How big is it? Does it have any of these security settings enabled? This is really useful information. And then I have these really nice tabs down at the bottom here, including strings.
Nice.
So one of the things I like about the strings analysis in Cutter, other than it's nice and clean, and I can also, kind of cut down to it. I can also look at different sections of the binary for what strings are in that section, which
Mhm.
can in fact be revealing. If I look, for example, things in the .text section versus what's
Yep.
in the .data section, whatever. So that can be helpful. But then, go ahead.
There are certain conventions for how data is stored inside of a portable executable in these different sections. So the .text section has like global variables. Maybe I always get that I need to follow the documentation for this. But basically, the long and short is that the different sections inside. Yeah, that's good right there. That's
Mm-hmm.
very juicy. The different sections inside the binary will contain different things. So some of the strings that are used as local variables will be in like the data section,
Yes.
and some of the strings that are used as global variables might be somewhere else. But it's always well structured. It always follows a certain convention that's defined as the portable executable structure. So yeah, getting kind of familiar with. Remember, it's all just bytes. When you break those bytes into different sections, where they are in the portable executable, getting familiar with where those things are, is super important. You may have just found one of the most important parts, which is something we should absolutely talk about. So when we go back to what I was saying about how a program, when it loads up, this is actually ties into the DLL order hijacking thing. Um, when you think about a program, when it loads up and it grabs onto different parts of the operating system and says, okay, I don't have all of the functionality that I need to run. I need to import a lot of this. I need to go to different DLLs, different areas of the operating system, and grab all of these different functions and stuff to be able to do what I need to do. So the there is a specific place in every portable executable that holds the imports from these DLLs, and they call it the import address table.
Mm-hmm.
And so when a DLL wants to pull in a function from another DLL in the operating system, maybe it's kernel 32, like we're looking at right now, it needs to know where that DLL is and map that to where the function needs to run inside of the its own PE. So the import address table, this is a bad example. I'll be very honest. This is a bad example because this is a NIM binary, and as I peel back the onion about how NIM like runs as portable executables when cross compiled to Windows, it gets weirder and weirder and weirder. So I'll just start with that. But let's pretend for a moment that this is like a C++ binary or something written in C. The import address table might be one of the most telling things that we can look at in static analysis because it'll tell you each one's of the API call that this binary is making at runtime. Now, if you're not familiar with the Windows API, it is a whole set of little functions that are written in different DLLs around the operating system that if you want to download a file from a URL, instead of needing to like work in the deep level of the operating system, we'll go ahead and just write an API call for that. All right, here, invoke it with this word, pass in these parameters, and there you go. You just downloaded a file. And API calls do all sorts of things, right? You see message box A right there, pops up a little message box.
Yep.
So all you need to do is know the name of the API call and pass in the parameters of the API call, and Windows will do the heavy lifting for you.
And by the way,
Mm-hmm.
defensive tools are looking at this too.
Yep,
So, for
for sure.
example, one of the things that you're going to get dinged for if you do a pretty traditional like interpreter payload or even really initial Cobalt Strike payload or something like that is if you're calling out to the create remote thread
Mm-hmm. Yep,
API call. That's going to get you dinged by most, if not Defender, certainly some of the more invasive
yep,
EDR tools are going to be looking at that. But even so, one of the things I like about Cutter is yes, it's showing me all of the imports and the functions that it's getting from each library. Then this is kind of fun from a even from a binary exploitation. Anything that's unsafe, it'll also
yep.
show me any invocations of this.
Nice.
Lastly, if I want to know where something is actually getting used, so for example, if I wanted to see where message box was getting used, if it is at all, I can show cross references, and
Yep.
that'll show me directly in the disassembly where this thing is getting called.
Nice.
And from there, I can, I can go to that location or I can copy this address, right? And
Mm-hmm.
then in my disassembly, I can go to that location, right? Cut right to it. I
Yep.
don't have to read the disassembly to understand this though, because
Yep.
when I am in this function, whatever this function happens to be, if I
Mm-hmm.
find the function list over here, right, whatever happens is sim.write to std error, right?
Yep.
I can show this in the decompiler,
Nice.
and it
Yeah.
will
Perfect.
use the Ghidra decompiler to actually give me a C-like syntax to understand
Beautiful.
what's happening. So
Nice.
super, super handy to be able to jump from a string reference or a function reference over into an actual decompilation of what the actual function is doing.
Now we're kind of getting ahead of ourselves
Sorry,
because
sorry.
we're a little in the advanced level. No, this is so good though because what I want to do eventually is talk a little bit about why we can decompile stuff. Like
Mm-hmm.
we see things that look it's not one for one the original source code, but like we're real close, man. Like we have a function name, we have the parameters there. And what you're going to find as we kind of peel back the onion on this particular sample is that the function names are quite telling, and I did that intentionally. But we're a little more in the advanced side. We haven't actually even triaged the dynamics of this yet.
Right.
So let's go ahead and let's put a pin in that, and we're going to fire up. Actually, we won't fire it up yet. Let's go ahead and drag this thing to the desktop and take a deep breath and double check all of our our configurations and then rearm. Oh,
Oh,
it's
that was
open in Cutter, so
the.
yeah,
Let's try that one
there we go.
ore
So
a
let's
time.
let's bring this. One thing I want to note the picture of Cosmo.jpg on the desktop. That's there intentionally. I write it so that the malware keys off of that picture. So malicious intention is achieved against that picture and that picture alone in most cases.
I really like
And
that the photo viewer UI has not changed since Windows Vista,
yeah.
obviously.
So yeah, just to keep it a little more safe, Cosmo.jpg has to be there. So let's arm this thing. Let's fire it up
Okay.
so we can arm. Okay.
Weapons hot.
And yep, weapons hot. And we're doing our initial malware detonation triage. We're going to detonate this thing and look at what happens.
Now,
And I want to
do you want the network simulator just
not
run
yet,
it? Okay.
intentionally so. Let's not get the network up and online
Got
for
it.
this. So we weapons hot, finger on the trigger, and we fire, and we wait, and we are like, what could this be doing? I wonder what this might be doing. And then this thing, if it will actually function the way that I wrote it to do, we just might have to wait, deletes itself from disk. Oh no.
Hmm.
So, well, if that was the only sample of that malware that we had, what just happened? We've
uh,
burned our sample, right?
yep.
So it's very, very important to have a restorative not snapshot in this case, although we could restore back to snapshot
Right.
if we wanted to. But it's very important to save this thing. Copy, don't move is what I'm saying.
Exactly.
If that's the only sample of malware that you had, if that's the only one that you had off the endpoint, if you, God forbid, you did that on the endpoint and it's gone now, big oof. You're gonna have to break out memory forensics now. Bad time. So
But
what
also
we
just
want to,
like don't do that.
yeah, and also don't do that. Yeah.
If we're doing forensics, for example, right, we're copying everything 3 times when
Yep,
we're
exactly.
taking samples. So the same thing would apply for any sort of malware analysis.
Yep.
You want to have a private offline storage where everything is saved to before you move it to your active lab.
Yep. So the lesson here is that make sure that your tools are up and running, because why did that just delete itself from disk? We don't know. But perhaps there is a reason that it maybe calls out to a domain, and then if it's not there, it deletes itself from disk. Spoiler alert. um, have your tools up and running. Have Wireshark up and running. Have if you're doing the network, remember I don't think I actually mentioned this, but in dynamic analysis, you're looking broadly speaking at host-based indicators and network-based indicators. If you're targeting in for your first round of analysis or for the first detonation, if you're gonna target one of those, make sure your tools are up and running for that. Really, we just did the initial det, which was that we ran it with no tools listening, no Wireshark, no internet simulation, and it deleted itself from disk. That's a pretty good data point, right? So let's annotate that, but then let's see under what circumstances we can coerce this thing to actually do something. So, yes, we actually have one of the answers now. So under what conditions can you get the binary to delete itself? We know one of those now. Initial detonation, likely with no internet simulation capability. It will, at least in the absence of the other tools that are up and running, it will delete itself from disk.
Mm-hmm.
We don't know exactly. Maybe it keys off another file that's on the file system, but like in the absence of us having our tools up and running to respond to any kind of request that this thing's making, it bounces like that. That's a good data point. Good data point to have. So let's annotate that.
Now, a question about execution. So
Mhm.
in the course, do you talk any at all about using kind of third-party sandboxes?
Yeah, so we'll
Okay.
go into like any run and Joe sandbox and stuff.
Cool.
That's kind of towards the end. And the sandboxes are great. Cuckoo is another one. I will probably I don't know if I'll have time to do that, to implement that, but I would like to. Sandboxes are great. But unfortunately, what they don't, one of the things that can fall short about a sandbox is that when you throw a malware sample in there, unless you're providing the arguments, if it's like looking for an argument as the from the command line, a sandbox might not have the capability to do that.
Right.
But yeah, sandboxes are really, really good for the initial kind of triage portion for the dynamic side. So we've got like Blue Jupiter for the static side and like a sandbox for the dynamic side.
Very cool.
So let's hone in on the network signatures for this binary. So let's invoke a tool called fakenet.ng, also developed by the Flare team. They're absolutely killing it when it comes to this stuff. Oh man, we got a lot of, okay, yeah, once it kind of calms down. FakeNet, what does FakeNet do? It is cool. It will handle all outbound HTTP, DNS, networking in general, any request that anything on the operating system is making. FakeNet will basically commandeer your network stack and say, I am the internet, talk to me. Excuse me. And when you detonate that binary, it will tell you where the network traffic is coming from and where it's going, essentially. So it will handle, and then it will save all the packets offline in a PCAP. But for good measure, why don't we break out Wireshark as well? Those are kind of the two things that I like to do. And what I might also mention is that there are other tools that do similar functionality that I teach in the course, like inetsim. Inetsim I like to have offline, like on a in my lab. I usually like to build Remnux and Flare VM and have Remnux be the like DNS server and basically the internet, the fake internet, and run inetsim on that. And then I think this is going to capture on the local host. So let's make sure. I think we need to be on the local host. But
let's see.
I think so. You can check. We can check this. This is an empirical question. Go to Google and type in any old random DNSrecord.com. and then we should be able to see if it's going to come all across on Ethernet 3 or if it comes across on the local host.
Honestly, even opening this up should make some
Mm-hmm.
noise.
Yeah. Yeah, and if you
I'm
try to go to
just
like,
seeing ARP, so you may be right.
I think it's on the local host. Yeah.
Okay, let me
So let's go.
capture options. Which one's
I
showing
think
me?
N. That's a good question. You've got a couple now. NP cap loopback adapter. Maybe.
It's gonna be one of these. I think it's. Let's go with the newest one here.
Okay, sure. Um, Now, if you go to whatever.com and FakeNet does its thing.
Okay, we're getting that. Nothing on this interface.
Okay. Weird.
So what I'm gonna do, there is an option to see. I'm seeing traffic on
You
Ethernet.
do see the spike. Yeah, that's weird. I think it's NP cap loopback adapter. Try that one.
Okay, we've got an ICMP destination unreachable. Oh, White
Oh,
Cyberduck, thank you
weird.
so much for the follow. Hayden Automate as well. Oh, okay, here we go. We've got
Well,
DHCP
that's
discovers, but that's.
DHCP discover doesn't mean a whole lot in the context of what we're doing. Yeah,
Let's
I don't
not
know. We'll
guess.
have
I
to.
think, let me reopen Wireshark. I think there is a way. Yeah, can't I just do all interfaces shown? Yeah, just go, right?
Let's give it a shot.
Yeah, there we go. So we've got
Well,
ARP.
maybe. We've got ARP, we've got DHCP. Don't have a lot in the way of HTTP.
Yeah.
Hmm.
So this is actually an argument for what I like to do if I'm setting up a full lab. So FakeNet has ups and downs, right? FakeNet's
Yeah.
super easy.
Yeah.
The other downside is that it completely hijacks your network stack, and trying to
Yep.
get other things to play ball with it, not super easy. What I like to do, I think is similar to what you were saying, is set up a second machine in the local lab network, and
Mm-hmm.
I'll have Wireshark running locally
Mm-hmm.
to capture packets. Hello, Lisso. Good to see you. Thank you for the resub.
Yep.
And then I'll use even Zap as an HTTP proxy that
Mm-hmm.
everything is getting pointed to
Very nice.
before it heads nowhere. if
Yep.
I care about HTTP traffic, and I'll also be capturing everything else that is going on. So there are lots of different ways to set up your network analysis stack.
Yep. And you can even do some really funky stuff with like Burp or Zap can then do like SSL interception. So
Yeah,
you can install a signed cert on the proxy and have it decrypt SSL as it comes in. That's more like 102 level, I think.
definitely.
But in any case, am I gonna have a Discord channel for my course? Yeah, it's gonna be. I have a Discord. I'm setting it up as we go. It's not quite ready for rollout yet, but yeah, there will be a Discord for it. Because that's what the world needs, another Discord. Oh boy. So, all right. So what can we do? Could we set up Remnux to hook it right into this lab? Do you think that would be something we could do on the fly?
I definitely can set up Kali to get the HTTP proxy for
If we,
sure.
yeah, let's go ahead and let's try that out
Okay.
because it's important to see the packets. Like we can trust what FakeNet is saying, but it's probably pretty important to see the packets. Um,
Okay.
so yeah, let's figure that out.
So let me get my Kali machine up. Here it is. This is so. Hey, look, it's the shellcode we
Oh
were doing
yeah,
the other night.
nice.
Um, so what we're gonna do, I have Zap open. So this is actually how we would do this. Let me make a new session. No, I do not. And let me just confirm that I am on everything that I need. There's Brain Pan
Hmm.
from Ginger Root's session. I gotta clean up my
Nice.
stuff.
Yeah.
But let me kill my try hack me VPN connection, and let me just head over to here. Let's close out of this. And let me just go to IPAS. I should have 10.0.1.5. Love it. So I do have a
Great.
and Oh, so to do this, if we want to do this without fake net, I might have to restart the machine because right, the network stack just got hijacked.
Yeah, probably. So I would just do a quick
Yep.
reboot. And yeah, we have not executed. Well, we executed it once. It would be best practice at this point to revert, but that might that might put in more issues than what it solves. So
Yeah.
yeah, we'll just go ahead and.
So let's talk a little bit about what's going on. So in my virtual lab here, I have a network, and let me actually go to my virtual switch manager to show how this is set up. So I have kind of a few different things that I have set up in Hyper-V, and you can do the same thing in VMware Workstation or VirtualBox. For now, it turns out Windows 11 is not going to support VirtualBox,
Mhm.
but whatever. So with my isolation lab, right, this isn't connected to anything, right? It's just internal private, no internet connection whatsoever.
Mhm.
Then my default switch, this is essentially, it creates a internal network that has a network connection. So it's a NAT situation. That's
Yep.
what it is. I do have a bridge if I ever wanted to have my virtual machines on my actual home network and I wanted to have that same address space. I have a bridge switch that allows me to do that. I almost never do though, unless I
Yeah.
wanted to
Sure.
like investigate an IoT device that I have
Yep.
that I want to set up. That's why I have that.
Yep.
Okay, but so with the isolation lab, right? So these are the two switches that we generally would use. And then if I look at my Kali machine, uh, if I look at my network connections, you'll see that there's the bridge. So it actually is set up to phone home,
Mhm.
but also it has an entry on my isolation lab. So because it has this entry in the isolation lab, and so does the Flare machine, these two
Mhm.
can talk to each other.
Okay. Excellent.
That's the plan. So we know that this thing has an IP, the Kali has an IP address of 10.0.1.5. Then we're back in on our Flare machine.
Mhm.
We'll load this thing back up. And actually, as it's going, I think it's 10.0.1.4. Indeed, it is.
Okay. Looking good.
So what is cool about that is that I can then set up Zap now. By default, Zap listens on the local host interface, right? It listens
Mhm.
on 127.0.0.1 port 8080 or whatever you've configured. However, I can also add an additional proxy listener.
Mhm.
Once the options open here. Come on, Zap, be a buddy. You're embarrassing me. Okay, so Flare's back up. That's good.
Okay.
Zap is being a jerk, so I'm just going to kill it and restart it. Of course, as soon as I go to
Which
shut it down, the options window
it's like, hey,
comes
I'm
back
here.
up.
Oh.
But that's okay. It won't take long to start back up. And this is going to capture HTTP traffic. So it isn't everything.
Mhm.
Um,
That should get us what we need.
but there are other ways. We won't do this today, but there are other cool ways that I've found to get everything off
Yeah.
of a Windows system to another destination that you want, which is kind of handy, especially if you're doing a Wireshark. Like you can set up a machine that does like IP packet forwarding,
Mhm.
right? And then so you can
Nice.
use Wireshark as it's essentially a router. Then it's capturing everything going through, so you can capture the whole smash without having to do fake net.
Yep.
Um,
Okay.
okay, so for this, what I want to do is configure my global, no, local proxies. So you can see the default is local hosted 8080.
Mhm.
What I'm going to do is I'm going to add, and I have some options. 10.0.1.5 is the one I want to listen for. On 8080
Nice.
is fine. Um, Now, with that set, I can now configure over in my Flare machine. Do, 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 do,
So we'll want to point this for the
proxy.
default gateway, I believe?
Nope.
Or how would we want to do this? Let me
So
think.
so Windows has its own proxy setting.
Ah, excellent.
Back in the day, you would have to do this in Internet Explorer,
Yeah, sure.
but now it has its own setting. So we're going to use a proxy server, return this on. The address is going to be 10 block 10.0.1.5. Yes, I use a 10 key keyboard. Um,
Got
and
my
port 8080.
6512 right here.
Hmm,
Ducky12SF.
very nice. I
No,
have a
no
DOS.
numpad to be found.
I have a full DOS keyboard situation
Nice.
because I'm actually not cool. I'm the squarest person you've ever met. Um, but okay, so now
Oh,
we have this
I
proxy
see something.
configured, and look at this. We're already getting data
Yeah.
coming in.
Oh, that's beautiful.
It's
Okay.
really, really cool, right?
Yeah.
So you're seeing all this stuff that Windows is doing just by being Windows. We didn't even do
Hmm.
anything on the machine. So we're getting our HTTP data coming into Zap from our lab, Windows lab.
Awesome. All right. So let's blow this thing up and see what happens.
Quick
We
safety
are.
check. I want to make sure with the reset of the Flare machine that my. Yep.
Oh yeah,
Okay.
you
Yeah.
didn't go back on NAT or anything. Yeah.
Nope. Okay. Just making sure.
Okay. Very important. Always, go slow, go methodically, double check. It does not hurt to double check. It does hurt to encrypt your hard drive on your physical host. So just be very careful. And yeah, I make sure to hammer that home in the course.
As my kung fu teacher used to say, slow is smooth, smooth is
Yeah,
fast.
slow is smooth. So that's in the military too. Slow
Yep.
is smooth, smooth is fast. And nothing hurts more than making a mistake that destroys your hard drive when you didn't intend to.
All right. So
Okay.
we're gonna go and get our sample again, right?
Well, we've got it on the desktop actually right there.
Oh,
So,
hey, look, it just got
yep,
rearranged.
unknown.exe. Okay.
There it is. All right. And so, drum roll, please.
Yep. Nice deep breath and run this thing. And we've got something. Okay. Fantastic. So, what did we just see?
Wait, we did?
Yes, we did. So, what from from the output, what does it look like?
Oh, whoa, what? This looks EC12 update. This is weird.
Mm,
Ubuntu.local.
interesting.
That is weird. EC12. I mean, this kind of looks like an AWS address, but not
Mhm.
totally.
Not quite, right? Yeah.
Yeah, but it's
Okay.
bizarre.
So we've got a get request to a weird URL, right?
Mm-hmm.
Is kind of what that ends up being.
For sure.
I'd say that's probably worth annotating. I think that's probably worth trying to figure out what that might be doing. Unfortunately, we do have a 502 bad gateway. So
Right.
let's take a look. Let's take a look at what happened on the host because we may have just found the answer to one of the questions that we've been answering. Where is the binary?
Uh,
Gone.
it deleted. All right.
Okay. So data point number 2, maybe 3. We have a get request to a weird URL, and if that get request does not return, if it returns 502, at least in this instance, the binary reached out to the URL and it deleted itself from disk.
Mm-hmm.
That's a pretty good data point. So
Definitely.
let's go ahead and annotate that as well.
Okay. Uh, so reaches out to.
Mm-hmm. And at least on a 502, deletes itself from disk. Deleted. Yeah. Deleted. Okay, another great data point.
And
But
we also have we don't have what URIs used to exfiltrate data. We can't get that, but
not quite, but maybe the first callback domain.
yeah,
Because when
exactly.
we detonated and we have that as a
By the way,
and as a
quick safety check. Bracket
oh
out
yeah,
them dots so
yep,
that it
there you
doesn't
go. Good
become a
job.
proper domain.
Yep, exactly. I even do the protocol at the front sometimes.
HXXP, yeah.
Yeah, be very safe. Again, a slip of the finger and you clicking on a link and the whole world comes down.
OreoByte asks, is that an active domain you can DNS query? No,
No.
it's a .local TLD. So
Yep. This is a safety measure in the context of the course. That will not a .local in DNS record land is very similar to a private IP address in IP space land, which is to say that a .local will resolve on a local area network if a host at that if somebody queries the DNS server and there is a host at that name on the local area or even LLMNR or any of those other funky kind of DNS query methods, it'll resolve. But you cannot go to what you see on the screen right now and register that as an active DNS record in like the greater DNS scheme. And so I do that intentionally. Remember, we're in an obstacle course right now. We're not on the battlefield, I guess.
Mm-hmm.
So a dot local is a way to make it as safe as possible, but still, if you swap that out for .com, it would be a potential evil address, right? Because like you can register any DNS name you want. So just because it looks like an AWS instance, but it's not, but that might fool people, right? So you can register that, and that becomes an evil URL that you can use to do all of your kind of cyber criminal shenanigans. But for the purposes of this course, all of the URLs that the binaries call out to are going to .local, and so that means that nobody can like pull a fast one on me and register one of them under DNS. And now my binaries are calling out to their servers. That's just a bad move. You don't want that. So we've got condition 2.
Okay.
What I think we'll need to do is get the working instance of iNetSim or Wireshark together to get, if we get a 502 bad gateway, what do you think might happen if we get a 200 okay? Is I guess the question that we need to ask now. And so let's see one more time if FakeNet will be able to run, because now we know this thing, when it runs and there's no network, it kills itself. When it runs and there is a network, it calls out to something, and if that is a 502, it kill or maybe some other stuff, it kills itself. Now we've got to ask the follow-on question, which is what happens when this thing actually connects to the DNS record that it's going to. So let's see if FakeNet will cooperate with us. And yeah, let's give it a shot. Let's fire this thing up.
And even if Wireshark doesn't play ball, we can go and check out the PCAP after the fact.
We can check out the PCAP. Maybe we could check the PCAP and see if we can get something. So
all right, very good. So unknown.exe.
And again, if we're doing, in the interest of time, we don't have to do this. But if we're being good scientific analysts, we will revert at this point to clean state, because we don't know if we've done anything else to it. But yeah, let's go ahead and just run.
Okay.
Excellent. Okay. Yeah,
So
this may be.
Yeah.
If that did not succeed, we might be running into FakeNet NG not playing nice. So yeah, let's see. Yeah, so it looks like failed to send outbound loopback TCP packet. So we're definitely trying to connect to that. In fact, we made an outbound request to that URL, and we're definitely trying to get that to call back now.
You think this might be why?
Possibly. Let's try.
Yeah.
Let's try that out.
Okay.
Other than that, I would like reset your network stack from the host, not necessarily the Hyper-V. Like I would go slick your IP stuff from the host itself and then try. And then we'll see.
Yeah, let's try, because it seems like that felt to me like a permissions issue.
Yeah, it could be. We've got a very interesting interaction taking place, and now we need to facilitate it so that it actually does. Diverter failing to call open service is actually fine.
Okay.
But yeah, we're on a lead. We've got a beat on something now. So yeah, let's see if we can coerce into thinking.
Well.
Maybe tap enter on the FakeNet window.
Yeah.
All right, it did not. All right, let's try one more time. Let's unpack the binary one more time and run it again, because it looks like it might be functioning now.
Yeah, I saw that.
FakeNet might be functioning now. Let's give it a shot.
Hey.
Okay. So yeah, we're getting a similar kind of error, and I think this is definitely like a FakeNet tooling error, which we would have to troubleshoot. But effectively, here, I'm actually going to fire this up so that we can move on, just in the interest of time.
Okay.
So you can go ahead. We're doing it live, as Chad says. I will share screen.
Okay.
I will move to here. Whoa. I had the infinite screen loops going.
Oh, I know.
At one point there. All right, unknown.exe. We're going to throw this right onto the desktop per usual. We will go to FakeNet. What's that? Oh, yeah, there it goes. So we'll get FakeNet running. And we'll just wait until we'll kind of tap through this until it you can just see all the other like malware workshop stuff that I've been doing.
Oh, I was sharing my screen. Let's try that again.
Oh,
there
yeah,
we go.
we caught caught in the recursion. And yeah, I'll pull it from the one that I sent you just so that infected unknown.exe. All right, with inetsim or fakenet-ng up and running, I'll go ahead and double click on this. And there we go. That's what we're talking about, ladies and gentlemen. So why don't we grab Wireshark? And I should have done this to start. So bad on me for being bad analyst. But boom, here we go. We now have like a heartbeat going on by the looks of it. So what this, and it might have been a little fast. But what we do is, the one thing that I'm not crazy about FakeNet is that it's so commandeering of your terminal. Like if you move, it'll just switch right back over to to the scroll, right? So check it out. Right in the middle there, unknown.exe requested TCP, and that's the FakeNet ng binary setting up kind of the internet simulation. It's requesting to update.ec2, et cetera, .local. And then after that, it goes to request for domain cdn.altimeter.local. And then from there, we have get requests going to /feed, and then with a post parameter, which is interesting, like get and post, but I guess in this case, it would be like a blog feed, like blog post. A post parameter of some very interesting information, right? And it looks like as this scrolls, we've got like roughly a just like stop there for a second by the looks of it. But we've roughly got like one request every second. And this data is definitely different, right?
Yeah.
So, okay, so we've got a dynamic signature that we can kind of hone in on. We now have 2 URLs of interest. So what are those 2 URLs to recover?
So we have the ubuntu.local one that we've already discovered, right? Which is kind of like the initial shout out. And now we have this altimeter.cdn.altimeter.local as the host with the full URI being /feed. And then the post, the get parameter, which is the post data.
Exactly. So little weird that post and get here, but that's, again, you could just say, okay, maybe if you would think of like a legit functionality of this, maybe it's like a blog feed site and the post is just the name of the blog. Like my blog, you could do like, you know, the name of the blog post to see that. But that's definitely, let me ask you something. Do you think that these are actual records? Like, do you think these are actual web requests somewhere, right?
Do not.
Seems a little weird. It seems a little weird. And it doesn't really even matter if anything's there. This could be return 404 for all we care. The GET request is still landing on the server somewhere. And as long as it lands on the server, that data is going to be written to a log file. And so we can hypothesize here, ostensibly, that's going to be like a log file that's writing somewhere on the server that they can just reassemble this data.
Exactly.
So we've now have, and if, let's see if I can coerce this to do its thing. The other, and again, just in the interest of time, if we do more in-depth analysis on this, the other way that we can get this thing to delete itself from disk is, let's say FakeNet is up and running. Let's say FakeNet is up and running, and we'll just give it a second to kind of think about, you know, get the config up. If FakeNet is up and running, and we kill FakeNet while this thing is running, this binary will also delete itself from disk. So that is
anytime
like,
it can't heartbeat, it goes
anytime
away.
it can't heartbeat. And you may be asking, like, what is this data? We don't know yet, but it's different per request, and it's happening about every second, right?
Right.
So while we don't know it yet, we do know that we can do this, like, so watch, it's running 1, 2, 3, 4, 5, Control C kill, and then let's see, and unknown.exe is gone. So if we had done a little bit more analysis to kind of like fuzz the ways that we can interact with this binary, that's another way that it can delete itself from disk.
Interesting.
So with that, I think the other portions of, and I'll actually stop sharing now because I think we're good to go back to the other one. But so screen and stop streaming. So with that, the other ones that I like to use in dynamic analysis for the beginning portion, to pull host-based artifacts, we want to look at things like procmon, which is a sysinternals suite. Super powerful. Oh my goodness, procmon is unbelievably powerful. It is, think of procmon like the most granular, the thing that can get you the most granular information about everything that a process is doing at any given point. And the real Procmon can be super overwhelming at first. The real power of Procmon is its filter criteria. The filtering
Yep.
on Procmon is so good. And you can get so many different things. If you go down to utilities
Oh, is that where
in
it
the
is?
Flare directory, yep,
Okay.
and then open up, you scroll down until you find Procmon.
Procmon. I was gonna say, like, there's no way this doesn't have.
Oh yeah. Oh, it does. And Process Hacker, that one right up there too, is another good
Very
one.
good.
There's so many good ones for dynamic analysis. We don't possibly have time to cover them all. Okay. Very, very busy when you open up Procmon because, like it or not, there's a lot of stuff going on in the Windows operating system at and then this is the defender's dilemma, right? Like, how are
Mm-hmm.
you gonna audit all of this, right? So if we go to a filter criteria, what we're going to want to do is go down to process name and then punch in the process name we know because we control that unknown.exe. And I'm just realizing that this is actually not, Procmon's not going to show us what we want out of this because the network stack. So remember, it's calling out to the URL, which fails, and
Mm-hmm.
then it deletes itself from disk. But if it succeeds, it starts doing the heartbeat. There are other host-based things that happen when that's going.
I see.
So I think I think we're probably going to be out of luck. But basically, what we would do, and we'll still get information out of detonating this thing with that set. So if we bring it out to desktop and detonate. Again, if we're being good analysts, we would revert back to clean state at this point, but in the interest of time, we will not.
Now there
Um,
is something else that we could do to
mhm,
simulate the call out,
mhm.
which
What do you think?
is, well, uh, so it was straight over HTTP, right? Port 80.
Yep, it's port 80.
So what we can do is we can add the cdn.altimeter.local
Mm-hmm.
to our hosts file,
Host file.
and
Nice.
then point that to our Kali box
Mm-hmm.
if we wanted to do that.
Mm-hmm.
And that would, let me just make sure that I can still ping stuff. Like, I don't know what
And yeah,
FakeNet did.
and what we would want to do is just put up like Python HTTP server. And
Exactly.
so it just needs to be something, right? And it's the Ubuntu like EC2 instance looking URL. We just need to have it grab onto something at that first request, right? So
Yeah.
that's good. That's real smart. So I actually do this in the course a lot. Your host file is super super powerful if you think about it because yeah, maybe weird Ubuntu EC2 instance DNS record out there might exist, but you don't even have to talk to that. You can tell the binary, hey, I am the local host, and also I am EC2 instance.local. And the binary is not going to know any different. The binary is going to say, okay, here's my GET request, boom. And that's like you've just tricked the binary into thinking it's connected to something. This is tricky. You might want to open up a commander prompt as admin and then nano down to the host file because
I have opened Notepad as administrator.
okay, fantastic.
Yeah,
Okay.
this is
So
a
yeah,
process that I do kind of frequently.
nice. Okay.
And that's because the lab stuff that I use at my work, right?
Hmm.
I'm using custom host names for it all the time, and so I'm editing host both on WSL and on the Windows side so that I don't have to guess because the two DNS resolvers do use both files.
Nice.
So for those of you who aren't familiar with the hosts file, this is a place that allows for static resolution of specific host names to IP addresses. On Linux, it lives in the /etc/etc hosts file. On Windows, it's actually pretty close, except that
Yeah.
that etc hosts is inside of Windows System 32 drivers. So if you want to edit it, you have to have administrative privileges, of course, and so you can do it, a bunch of different ways. The way that I find really easy is just opening Notepad as admin. Now I can get to that folder. Here's my host file, and you can see there's
Excellent.
some examples here. So I'm gonna take uh right, what is it? It was CDN.
Well, so we've got two of interest now, so we can put
Right.
both of them in there.
Right.
And so what we want is and
Uh
it's just the host name. You don't need to specify protocol. So it would be well, you have it in your notes. Just copy it out. It's the weird AWS looking one,
yep.
right?
So 10.0.1.5 is where my destination is, right?
Yes, because
And
that's going to be Kali.
right. So then cdn.altimeter.local is one of them, and then the other
Yep.
one is this guy.
Good. Very good.
And so Um, we're gonna toss that in there, get rid of the
Mhm.
brackets because now we actually want that thing to work.
Yep.
Tab that
And same
over.
same idea. We can throw that to 10.0.1.5. Remember, so all of this is just rerouting. It's doing a little like shell game almost with the network information because the binary is dumb. It's been programmed to do exactly what it's been programmed to do. So you can just change the things around it, and it will think that it's connecting to CDN altimeter or the Ubuntu one.
And you can even see
Um,
this now that I've pinged
yep, perfect.
cdn.altimeter.local. I'm getting
Oh, beautiful.
10.1.0.5 back. Now,
Now,
over in Kali.
yep, there we go.
Okay, so we have this proxy coming up, and this is actually rad. What is all of this?
Oh,
Um,
baby. No idea.
what are you doing, Windows? What are you doing? But so we've already proxied all HTTP data, right? We already
Mhm.
have done that. But um, oh, actually, that should solve. Shouldn't that solve it?
Well,
Because the
maybe.
resolution is gonna work now.
Yes, the resolution will work, but there's nothing on the other end, right? You might get a 502 bad gateway again. So what we need to do is just stand up the Kali HTTP server to catch it, and just as long as it gets a 200, I think we can coerce this thing into responding.
So we have to kill the proxy to do that
I think we would have to kill the proxy.
because
Yeah.
the proxy doesn't know how to handle itself. You know what I mean?
Yep.
Okay. So if we want to do that, we're going to turn off the Zap proxy for Flare and just
And
use.
this is by the way like fantastic. This is all really good troubleshooting and like good skills to have in terms of like, okay, how can I coerce a binary into going to where I want it to go to and doing what I want it to do? A lot of you can modify the things around it, and this is what we're doing: the host file, setting up proxies, setting up an HTTP server. In the course, I teach how to build a little Python server to just respond to very specific network packets that are coming across.
Yep.
So yeah, it's all about just remember you when it's in your domain, when the malware ends up in your domain, you're the master of your domain. So you can trick it into thinking it's going to its actual intended target when it's not. So yeah,
Yep.
let's see what we get.
So
All we need to do.
to recap what we have set up currently, we have taken off the Zap proxy, meaning that we aren't telling the Flare Windows system, like across the board, send all my HTTP traffic to this proxy. We're not doing that anymore. Instead, what we've done is tell Windows, hey, cdn.altimeter.local and that crazy Amazon
Hmm.
domain, right? This right. Whenever you get any requests, network requests that are there, don't worry about DNS. We already know what
Yep.
it is. Send it to
Yeah.
10.0.1.5. Now,
Yep.
because what the binary is going to be doing is sending HTTP traffic, because we no longer have the proxy set up, we need something on Kali to catch that HTTP data. HTTP's default port is 80. That's what it's going to try to send to over the network. So, what we now have set up on Kali is I'm using Python's built-in HTTP server running
Perfect.
on port 80. Now, I have to run this is sudo because ports underneath 1000 are privileged. So you have to use root privileges to make that run. Once it's running, anything that is HTTP over here is going to fire up. And before we run the actual payload or the actual sample, I'm going to do a quick test.
Hmm.
The way I'm going to do that is with my old friend invoke web request.
Nice. A legitimate use of invoke web request,
This
ladies
is
and
the
gentlemen.
only legitimate use.
Put it in the
So
museum.
we're going to do invoke web request, and this can also be shortened to IWR. Give it the URI of http://cdn.altimeter.local. And then we're going to go back over to our Kali machine, and you
200.
can
Okay.
see that I've gotten a talkback
Yeah.
from 10.1.0.4. So we know that we have
Excellent.
communication between these two points.
Now, it helps to revisit why we're doing this. What is the current indicator that we're after? And it's not network. I'll give you that much.
Right. So we want to know what the thing is that's getting exfiltrated.
That's a good, yep. We want to know what it could be, what it's doing with those post requests, and we want to know when this thing runs, what is it host base wise? What are we after? But to do that, to answer that question, we need to have the facilitating conditions to get the binary to execute in the first place. So
Now,
let's give it a shot.
Will, question. Not this is a little bit reading from the back of the book, but
Yeah.
does the binary require a 200 or will a 404 suffice?
I think I think a 404. Well, that's a good question, but I guess we'll find out.
Okay.
I think it is. I think a 404 in the second part should be okay. So,
Okay.
but we'll see.
Because if it needs a direct, it needs a success. That's a little bit trickier. It's not impossible,
Yeah,
but we need a
exactly.
little
Yeah.
bit more work to do.
Yeah.
Actually, we could do that one in NIM. Just saying.
Yeah, exactly. So that, yeah, like remember that the altimeter was a get request, right? So that might just be getting from the server, and then it'll give the 404, but the data is still going to be there. Like it's still just going to say, hey, do you have this? Hey, do you have this? Hey, do you have this? And the get request or the response is going to be nope, we don't. Nope, we don't. But the data is still there in the body of the URL, right? So all right,
so we're
let's
firing
fire it
off
up.
unknown.exe. I'm hitting.
Remember, we have Procmon. We have Procmon in the background.
Oh,
there we go.
okay, so
Okay, perfect.
404s.
Yep, that's actually fantastic because look at the information that's coming across. So yeah, so we've got like look at the first thing that happened.
It did delete itself though.
It did delete itself because it stopped, right? But we were after host indicator, so we did trigger it that 120608 get slash HTTP1 that 200. That was the first request. It doesn't say the URL, which is unfortunate. But then it says get feed post and then some amount of data. So it definitely did run correctly, and it probably just hung after 404ing a couple times.
Yeah.
But that proves the concept. Let's go back to Procmon and see if we pulled anything off of the host for the endpoint. I hope Procmon.
It was running.
Yes. Okay. Beautiful. All right. Procmon there's so much to Procmon. Generally, I like to look at file creations, file deletions, handles on files, which could be there'd be a whole lot. TCP, you can get, and this is like some indicators straddle the line between host and network. You can get TCP connections outbound from Procmon based on the host activities that are going on. So yeah, what we're doing is operation either contains or is, and you can do TCP send and add that in as a criteria. Remember, our process name is unknown.exe, and look at that. We've got our TCP outbound connections there, host-based indicators that infer network activity coming from the host. Super, super important. Now, one thing that we want to, and again, in the interest of time, reading from the back of the book, this actually unpacks a file somewhere on the operating system. And we saw a string that we could infer where that is and what it might be doing. Do we remember what that string was when we pulled the strings?
It was, well, I don't have to remember because I had a notebook.
We wrote down. Yeah.
that was taking notes for me. I didn't even have to take notes because good old Blue Jupiter, or actually good brand spanking new Blue Jupiter, took notes for me in the string sifter out.log. So nice. C users public password.txt.
Second from the top. Okay. So for a lazy malware author, now it's something that's very interesting that I'll point out as an aside is that altimeter showed up in the URLs, but Ubuntu AWS looking one did not. And that's actually intentional. If we go into the decompiling part of this, and I don't know how long you want to run this one tag, so I don't know how much time we have left. We might want to cut right over to that. It turns out that there's actually like an obfuscation routine that runs to remove that one out of the strings and assemble it at runtime. So
I think
we'll
end on doing cutter and like doing some of the decompilation.
Yeah, sounds good. So why don't we go visit C users public password?
Well,
so again,
and before we do that, real quick, I just want to actually remove the operation filter, and I want to change it to file write. To see if we can see this in process monitor. To create file is what
create file. And create file is particularly noisy, but we do have a string to hone in on. So let's go ahead and see if we can well, hey, congratulations. We got a winner. So yeah, that's your create file. And then if you look, it succeeded, and we have a file created in the operating system at the public directory. So if we motor on over there, we should see something. And what could that be?
Ooh,
Password.txt. That wasn't there before. Awesome. Okay. So to recap,
that's something. There's that a question. What is the password?
I think it might be what's the key in use, right?
Oh yeah.
Um, we now know the URI that it's exfiltrated to. What's the key? Sicko mode, which is unpacked at runtime and read from the read by the binary from that file. It's not. It's in the binary as a packed file, and it unpacks.
Very cool.
We do know the URI. We may have some inklings of what type of data is exfiltrated, meaning like the how exactly the file's data is transmitted. It's get requested with a parameter in the URI. And then the type of encryption, the algorithm in use actually is not clear to us, but it will be once we start cutting into this thing.
Right. So speaking of,
Yeah. So we are now, and I think we'll wrap up on this one. We've crossed into the advanced static analysis with the capability to do advanced dynamic analysis. I know Cutter has the debugger or the debugger. The difference
kinda
between
doesn't really work.
advanced static and advanced dynamic. Static, again, you're not running the binary and you're decompiling and disassembling. And in advanced dynamic analysis, you are debugging. You are putting this thing into a program that can step through the actual execution of the program, and you have complete control over it. So you step on each of those instructions.
Yep.
So, okay, let's motor over to the decompiler.
Okay, so with before we get to the decompiler real quick, I just want to say,
Yeah.
so again, when we open up Cutter, and this, again, as you said, this is kind of getting more advanced. So learning how to step through a binary in disassembly or anything else like that takes some time.
Yes, this is I think of this a lot like music theory.
Hmm,
And that's a good analogy for a lot of different things in the cybersec space. Networking. It you see like session musicians just like they can pick up chord progressions and be like, oh, I know, and they can solo right over it, and they can just kind of like they intuit what's going on, and they didn't start that way.
right.
If you have no experience with, if you're looking at the screen right now and you're like, this is scaring me and I want to go home, I was there too, and I still am there in a certain sense. The session musician didn't start out being able to solo over those chords. It's just practice. It's getting in here and looking at things. And the more practice and the more that you look at these things and start to see the matrix a little bit with how this stuff works, you begin to intuit how these things are actually working.
If I
And
may,
so, yeah, sure.
so it's funny you mention that. So next Friday, I will be delivering a talk at ShellCon that is about how to self teach
Yeah.
in general. And there's a lot of ed theory that goes into that, but I'm breaking it down into 4 maxims basically that we can use to guide ourselves. One of them is language precedes understanding. And one of the examples that I love for this is the Einstein field equations.
Mm-hmm.
Um, I had a real block with math when I was in school. I still do in a lot
Hey,
of
man.
ways. But one of the reasons why, and I think it's worth understanding, is what happens in your brain when you look at something like this and you don't know what's going on. Your
Yeah.
brain just it just
Yeah.
shuts down because there's too much new information for you to process, and you cannot parse any meaning out of what this expression is. The
Mm-hmm.
same thing is happening to you. Like if you look at this, if you are a particle physicist or a theoretical physicist and you can look at this like respect, um,
Mm-hmm.
but if you wanted to learn how to do this, you would have to break it down into its component parts, understand like what R is, what the mu is, what the pi is. Pi we might be able to figure out, but like what each of these symbols means, and then put it all back together
Yep.
to extract meaning. And it takes a full comprehension of the language behind it. So until you have a full comprehension of a language, whether it's music, whether it's mathematical notation, whether it's assembly, the first time that you look at information in that language, you will not parse it all. It's
Mm,
okay to not
yep.
be parsing it all. Um, and that just, as you said, it takes time to learn how to extract meaning from these things. So
Yep.
it's okay to like feel that just like overwhelming sense of I don't understand what any of this is.
Mhm.
Let that kind of wash over you, and
Yep.
then try to break it down into the parts that you can read, and then understand where the next thing you need to learn is.
Yep. That nailed it. Absolutely nailed it. And yeah, it will take time, but remember what I said at the outset of this. There's still a space for you in this skill set and in this discipline to look at this and say, I don't know what I'm looking at, but that's okay. There's still a space for you to apply the skills that you do know and study the skills and study the language that you're looking at and say, I'm not sure what this is, but we're going to start to tease it apart. So what Taggart is doing right now is actually where I was going to start. And I think you should always start at the start. And the start of a portable executable, in most cases, is the main function. And so what
Okay,
we're looking at right now, why
I can
can
make this
we
bigger.
Okay, yeah. Um, why why can we take something that we're looking at right here, which is assembly language, and recreate it into something like the decompiled output, which looks pretty close to a. And if we just grab like a, yeah, we'll just have to grab like a thing. Um, what that looks pretty. It's not quite source code, but it's pretty close, right? Like that's kind of a higher level language. If you think of like high level languages are very abstracted, in spite of the fact that C, the language, and C++ look very technical and cryptic, they're actually quite high level when it comes to comparing it to like the deep stuff in the operating system. Um, why is it that we can take the really low level stuff when we're given a binary? The malware author is not going to be kind enough to give us the source code. I gave it to Taggart actually, but that's beside the point. Um, the malware author is not going to hand you the source code along with it. They're going to give you the binary. They're going to give you the binary. And the binary is just bytes. The binary is just when you break it down, it's just little tiny little pieces of data that make these little primitive instructions that tell the operating system what to do. So when we have that, we need to like actually, in a literal sense, reverse engineer that and just whoosh, like that. Like you basically start with these tiny low level instructions, and we're not like, you don't need to know like all of the instructions that are happening with the assembly. You can interpolate the meaning of those assembly instructions and bring them up levels of abstraction into the higher level languages. And so in and it's different per language. Some
Mhm.
languages you can, because of just how they're made, you can get basically the source code from them like that, right? In C, in C++, in nim, because nim compiles basically right down to C.
Mhm.
The best we can really do is this kind of like approximated decompiled output. And in most circumstances, that's actually going to be fine. So, all right, we have a binary, and we have it in the disassembler, and we're looking at the reconstructed higher level language. So we start at the main method, the method from which all other methods in a program are called. And so when you start, when your operating system is humming along and you double click on a binary, the operating system basically breaks from its execution, and it says, oh, hey, we've got a binary on our hands. Let's hand over execution of the operating system to this binary. Let this binary do whatever it needs to do. Start at the main method, or the entry point, really. Start at this first method and follow this thing through and see every other thing that it calls from there. And basically, if you think about it, like it's like well, let's say like I'm sitting down and I'm studying and I'm recording a video for my course, and then my partner Emily comes in and she says, "Hey, I need you to go to the store and pick up some eggs." So then I go, "Okay, I will stop what I'm doing," and I go to the store and I pick up eggs. And then on the way to the store, maybe there's a cat in a tree that I need to save, and somebody says, "Please save the cat in the tree," and I go, "Okay, I'll do that." But once I'm done with that, I will return back to what I was doing before, go to the store and pick up eggs.
So
So
process
then I
execution is side quests.
Yes, it's side quests all the way down. So it's basically you start at the function that was being called, you go to the next function that's called, and then you drop right into that. You step into that function as it's being called. You do whatever that needs to do, and then you return out of that function. But what if that function contains more methods that are called? So again, if I'm on the way to save the cat from the tree, maybe somebody comes up to me and says, "Hey, I have some very interesting information to give you about yoga." Okay, I talk to them real fast. Like, okay, very interesting. Thank you for the pamphlet. I finish what I was doing with them. I save the cat from the tree. I then finish what I was doing there. I go back to get the eggs from the store, and it just you unravel it all the way back up, and that's basically what like a Windows execution will do when it's double clicked. So what I'm saying is that we've got like a Matryoshka doll situation of methods that are being called from the single entry point that starts. So if we don't even really need to worry about like big specifics of what are going on. All we really need to do is start to look at the different methods that are called from the main method, and we can start to unravel what this program is doing. And there's a good graph indicator or a graph representation of this too. And I think we can open this up now. And let's go a couple method calls into the main function and find, I think, the nim main inner.
Yeah.
And if we go into the nim main inner, so basically the portable executable says, okay, I'm setting up a bunch of stuff. It sets up a lot of preamble that we don't need to worry about. And then it gets something like this. And this is super, super interesting from a reverse engineering perspective. Again, you may be looking at this and you're like, my eyes, please stop this. I actually like the color scheme of Cutter. It's very nice.
Yeah, I don't hate it.
So right now I am, and it helps that I wrote this, but
Does it?
I'm soloing over this binary right now. Like I see the chord progressions, and I'm going like, okay, so we start right here, we go into this function returns, and it comes right out. But if you're not familiar with how the binary was written, this can all be really telling. Do you see anything, Taggart, that really stands out to you right now?
So I see a bunch of things that call out. The first is anything. My brain is trained at this point to look for function calls. Now they're
Mhm.
orange in Cutter, which is helpful, but I'm also looking
Nice.
for words that I know. So for example, get current dir. Now I'm thinking, okay, so they're getting the binary is performing recon about where it is on
Mhm.
the system.
Okay,
Uh,
that's a very good assumption. Yeah.
right? And now this check kill switch. First of all, my brain is going to
Oh,
see anything with the word kill in it and be like,
excellent.
what is that? And so from here, I would probably just double click on check kill switch because I know that this isn't inside a conditional, right?
Yep.
I'm not inside an if curly.
Mhm.
So this thing is just getting called as part of nim main inner.
Yep.
So what up?
So
Um,
it does, but it does. Oh, and you jumped into that, right? So go into. Let's see if we can go into graph representation of this one. Actually,
it's not
go.
graphing. Oh wait,
It's
yeah,
not
it is.
graphing.
Yeah,
No,
it
there
is.
it is.
Okay, so nim
Okay,
main inner does
so
graph.
all right, so remember that there are a lot of like conditionals at play in here. So like if something happens, do this. If something else happens, do this. That's kind of how programs are written. So we've got a bunch of conditionals, and the way that this actually is accomplished is a little technical and a little low level. But at a when you write an if this do this in something like C or nim, else this do this. At the assembly level, basically, it's manipulating the very low level memory registers, and then you get something like a jump instruction and say, okay, test AL. And I know what. So AL is the lower bits of the accumulator register, which is not really something you need to, or it's the 16, the 16 bits of the accumulator register. You don't need to worry about what that is, but basically it's testing the contents of that register.
Mm-hmm.
And the JNE instruction right after that is going to say if it's 0, jump go to this. If it's not 0, jump and go to this. So that is a low level representation of something like if this, do this, else this, do this.
And
This is
do you see how this memory address here matches what's at the top of this
Yep,
cell in the
right
graph?
there. Yep. So jump if not equal to. And again, as you study assembly, and we just don't have the time to like go into like all of the stuff about assembly right now, but
Mm-hmm.
as you study assembly, this stuff starts to unravel itself to you. Okay, jump if not equal. If you test the contents of this register and it's 0, go this way. If you test the contents of that register and it's not 0, go that way. And so this is what the graph representation basically breaks down. So we don't really know what we have. Check call, check kill switch URL. If you go up a little bit, this is a very good example. So in that block and just down a little, we've got the call to check kill switch URL.
Mm-hmm.
And then whatever that call returns, we move the bytes of that call into the AL register. So we've got MOV bytes, and then the operand is it goes it goes instruction,
Destination.
destination and source, right? So it's
Yeah.
a little counterintuitive. It's just something you have to learn. Move the contents of AL into the location that I specified, and then test the contents of AL. Test is a non-destructive comparison to see the contents if it's basically like a 0 or a 1. It tests, and if the content matches, it flags a 1. And if the content doesn't match, it flags a 0. This is all a little more technical than what we probably want to go.
So no, it's good though. So Angel is asking, like, why is test comparing the same register? So
right.
A little bit of programming experience does help with this.
Yes,
because
it absolutely does.
You start getting a little bit of intuition with oh, hey, CQ, thank you so much for the hosting. Really appreciate it.
Nice.
So what's really going on here is the function basically returned true or false. That's what we're looking at, is a check that is a Boolean. And it's either 0 or 1. And that's why test is checking itself to see if it's 0 or 1. If it's so we're looking for a true or false value. If it's true, we're going to do one thing. If it's false, we're going to do another thing. That's why it's testing itself.
Yep. And Taggart, I don't think you know the source of this particular one. Like I
haven't seen it at all.
So yeah, you absolutely nailed it. Check kill switch URL returns a true or a false value. That just the same way as if you're writing a high level language and you say, okay, if you do this function and it returns true, do this. Else, do this. We're looking at the exact same thing in assembly right now. It's just a little more fine grained to say, okay, to be able, the processor is saying to be able to tell if that is a true or a false value, I'm going to move a value into this register. And then I'm going to test that register. And if that register is a 1, I'll do one thing. And if that register is a 0, I'll do another thing. It's like a super, super primitive computer, because it's a very, very low level way to look at like programmatic syntax. But yeah, so what happens? So let me just in this code snippet right here, what happens if we do not have a 0 in the in AL at the time this instruction executes?
So we move over here to this address and this block here. Mm-hmm. And so it looks like we're doing a little bit more work. Now, we're loading some stuff into a register from places in memory. We don't know what that is just yet. This all looks like, preamble to a function call. We're setting up arguments to a function. We're calling set jump. We don't know what set jump is yet. So then we're then going to compare another test, at which point, so this maybe is like, just again, some intuition from having looked at a lot of programming before, is check kill switch URL. It's like, if this thing is set, then we're going to just go and fire off the thing that we know. If it isn't set, we have to do some pre-work. And then once that's done, we're going to test again and then try some other stuff.
Excellent hypothesis. I will say from the back of the book, you have it inverse.
Oh, okay.
So remember, check kill switch URL returns a Boolean value. If that Boolean value is 0, what does that mean?
Oh, if it's false. Okay, right.
So if the Boolean value is 0, that means that it returned true. If the Boolean value is 1, it means it returned false. So jump if not equal, meaning jump if there is a 0 in there,
so
says,
if it's true, right?
If it is true, continue on. And we've got a lot more going on by the looks of it, right?
Yeah,
like
for sure.
Like we see unpack resources, steal stuff, pop safe point. It looks like there's more to the program going on. On the other side of that, if it is a 1, if it's not equal and it returns a 1 in the contents of the AL register, what calls or what takes place, I guess?
So we're calling the Houdini whatever function.
Houdini.
And then we're jumping right down to kind of the end of this graph. This address here. We're adding to the stack pointer. We're popping, and we're returning. So we're getting basically out of this subroutine.
Exactly. So I think that's probably the furthest we want to go, because that might be the best the best illustrative point of how the decompiler and the disassembler are going to aid us in this quest. And I don't want to inundate with information
Hmm.
because this gets pretty.
Well, you also want people
Let
to
me
pay
put
for
it to
the
you this
course,
way.
right?
Well, sure. Let me put it to you this way. I still struggle with this stuff, and I've been doing this for a while now. And it's a journey in very fine grain, very rudimentary computing. Not like the computing that you and I are used to from today's standpoint. Not like the I click a button and a thing happens. It's like we need to set up how this program is executing. We need to move data around so that we can start the execution of whatever we're going for. But we do see that the disassembler slash decompiler gives us a ton of really good information. Even if we're at this low level, we can still get some of the high level functionality. We check a kill switch URL. If the kill switch URL returns false, we go to Houdini. Don't quite know what that is, but we can infer by the name maybe and the fact that the binary deleted itself. Maybe that's the self delete, right?
Hmm.
But if it succeeds, the program continues. Then we go down and we say, okay, we test a few more conditions, and if we jump if not equal, and we go to a couple more function calls into unpack resources, steal stuff, and then pop save point.
Hmm.
So it's I guess what I'm trying to say is that as you get more familiar with this, the real very fine-grained specifics are going to reveal themselves right around you. And
This
the more
is
you stare at it, the more you kind of start to unravel it. But even, and I think there may be some people that have never looked at a debugger or a decompiler at this point, you probably already have a pretty good idea of what this program might be doing. Check the kill switch URL. If that works, go unpack some resources, go steal some stuff, and then of course, like it helps that the names of the functions are a little indicative. But the only difference between you understanding it per the name of the function and understanding it per looking into the function and seeing how it functions is just a deeper understanding of assembly. That's all that separates it. So you can. This is the true reverse engineering. This is the I took something that I knew nothing about, and I now know the general programmatic flow of the program at like a high and at a low level. And so if you can do that, and again, let me preface this by saying, or let me add into this, people make their whole careers out of this stuff. So it's deep and it's intense, but it's super powerful when you can get this stuff down. But I hope that that's a pretty good introduction to like what a disassembler can do and why one could be useful when you're trying to say, I know nothing about this binary. Let's see how it works.
absolutely. And coming back to the idea of malware analysis, like as a blue teamer, this, even if I don't have time, because look, sometimes I don't. If I don't have time to go to full depth, like to do a full reverse engineering on a real sample. And by the way, if you try reverse engineering some like real live ammunition, it can be even more complicated than this. So it does take
Absolutely.
time.
Yeah.
Um, what fascinates me about this and why I got so excited about learning this in the first place was, to me, I mean, all technology is exciting to me. I just love learning about how all of this works. But what is so cool about assembly in particular is that it's the truth, right? Is it
Mhm.
is the
Yep.
absolute truth about what the computer is doing at the metal,
Yep.
and what the instructions that the processor is actually executing are doing. Now it takes time, much like resolution of a map. You're at 30,000 feet. You have a certain resolution of a few square meters or a square kilometer. You zoom in and you get a better resolution to understand more about what you're looking at. You zoom in and zoom in and zoom in. But as Husky was saying, even without getting into the specific assembly, even looking at the path that these things take, or looking at the decompilation, looking at a higher level language, you can understand the picture. You can see the outlines of the map and understand the how and the what of what's going on.
Mhm.
So super exciting work. Husky, thank you so much for this introduction. I think I'm excited to take the course for one. Can you
Awesome.
remind folks where if they want to know more about the course, where to look when it comes out?
Yes, so just stay tuned. I'll certainly be posting it on Twitter. I'm sure Heath will as well. I'm going to make it available to TCM Academy. I don't have any plans to release it on other platforms at this point, and that's really just because I'm a full time. I do offensive work full time. So I'm trying to. I'm actually weirdly enough, I'm trying to keep the student pool like not huge, just so that it's manageable for me from like an instructor standpoint, because I want to be there with the students and answer their questions and stuff. It should be released on TCM Academy. I've put a tentative release date for, let me take a look at the calendar real quick. Tentative release date for the weekend of the 23rd of October, I think is what I'm going for. So stay tuned there. I'll certainly be posting that on Twitter. And I really hope that like what I'm really trying to go for here is to banish that fear that I'm sure that I had when I was a couple years ago trying to figure this stuff out, and that I'm sure a bunch of people have looking at something like reverse engineering and malware analysis and say this stuff is not esoteric. It's complicated, and it's a different way to look at computing, especially at the lower level. But there's a bunch of stuff that you can figure out from the higher level as well. There's still value to be had. You can still write Yara rules and Sigma rules based off just the basic dynamic and static analysis alone. So get in there, get armed up, go bring the fight to them, right? Impose the cost on the malware authors.
Okay, Andrew.
And yeah, and just yeah, that I'm really hoping that I can bring that demystify and clarify some of those concepts to newer people who are newer in the malware RE space. So yeah, so yeah, that's the
Incredible.
plan.
So Husky, thank you again for coming on and sharing this with, and coming on Wednesday to do some NIM malware. We'll
Yeah,
hope to see
this
you
has been a
again,
blast.
certainly.
Oh, you know it, man. Anytime, anytime.
For sure. And so, Husky, where can folks follow you on social media if they want to see more of your adventures?
I'm not used to answering this question yet, because I didn't have a Twitter for a long time. At HuskyHacksMK, go to huskyhacks.dev. That's my kind of like blog website. God, where else am I? I don't even know. Find me on. I'm in so many Discords at this point. It's nuts. And then there will be a Discord released for the course itself. Email me. Yeah, just say hi, ask questions. I love talking to people. Yeah.
Certainly, Husky is a frequent contributor in the Taggart Institute Discord. So if you're not in there, jump in there.
Adjunct staff,
That's
adjunct
right.
professor.
You have faculty status now. So until next time, let's check out the hack list. If you don't know about it, there it is. Let's see if we have anybody else who's streaming that we can give a raid. It looks like Savitar is going right now, so let's go ahead and raid Savitar.
Awesome. Thank you so much for having me on. Thank you everybody in chat. Yeah, I hope to see you around the Discord. If you have any questions, just send me directly and let me know.
All right, friends, until next time, be good to yourselves, be good to each other, and we'll see you next time. Happy hacking.
See you guys.